Hello, everyone. Welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen, Associate Professor in the Department of Chemistry and Biochemistry at Florida State University. I do all things light matter interaction, photons driving processes like photocurrent generation or photomechanics. But more importantly, joining me today is my guest, Dr. Christianne Beekman. Christianne, if you wouldn't mind introducing yourself.
Hi, I'm Christianne, and I'm an associate professor in the physics department at FSU, and I work on thin films of magnetic materials, and mainly materials that are actually magnetically frustrated. Now, if you want to know more about that, please ask a question. They're highly interesting materials that could be hold future applications in quantum computing. So I'm highly interested in manipulating their materials properties.
It's exciting. What do you typically teach?
Oh, I teach condensed matter physics to undergraduates, and also sometimes astrophysics to like non-science majors, and sometimes general physics, and so it varies.
Yeah, that's fun. All right, what game are we starting with?
Super Mario 1.
Super Mario 1. We're going with an all-time classic, ladies and gentlemen. Super Mario Brothers 1. Just some casual teaching of astrophysics, you know.
Not my field, but you're gonna.
I honestly like those more because you learn something. You have to in order to teach it, which is kind of fun.
I feel like I probably have the right level of knowledge to teach non-science majors astrophysics because I don't get bogged down in some details maybe that others do get bogged down in, but who knows?
I mean, you know what it's like not to know and not fully understand. Until that student asks the really hard question that.
Well, and sometimes there will be a question that I just don't have the answer to, and then, tell them and look it up later and explain next week. But that can happen with anything. Yeah, it's actually fun to teach astro, but I do prefer to teach condensed matter. Then I can draw on my knowledge from the lab and a little bit more than with astro.
Yeah. I like the balance of undergraduate plus graduate specific versus general classes. It's nice to mix and match.
I would love to teach graduate students condensed matter, but there are too many others teaching that and that want to keep teaching that, so I have to wait my turn.
That's fair. Triboluminescence opening with the questions. Not even giving you time to settle into your gameplay. It's fine. You got some practice. You're feeling okay with the...
Go ahead.
It's coming back.
Not really. Look at that.
Yeah. Well, you said earlier it's been 20 years since you played this,
correct,
right?
Yes.
Yeah. That's fine. It's like riding a bike. It'll come directly. But you probably did a lot of when you were younger.
Correct. Yes, I was very happy when I got the Nintendo.
Yeah.
For it's a Dutch holiday actually that I got it for.
Wait, which holiday?
It's called St. Nicholas, and it's essentially right before Christmas. 2 holidays in December over there, so which I wasn't unhappy about as a kid.
One might assume you guys were born with bikes, given the prevalence of biking.
Yes.
It's just everyone. It's probably pretty crazy coming to the U.S. and nobody's biking.
Well, but would you want a bike here?
I do.
Well, I would fear for my life.
Yeah.
I fear for my life.
No, I do bike in, but I do it at 6 a.m. And there's no cars on the road. It's
That's
safer.
pretty safe.
Yeah. But you're right. The bike home is not an easy ride. All right, Triboluminescence, which I can reveal his name now because that's Steve Leonard, actually.
Oh, okay.
He wants to know, how big is the universe?
Well, I mean, how big is the observable universe? That's like 13.8 billion years.
Oh, you got it.
What's beyond that? Yeah, that's who knows, but 13.8 billion years is what we can see, right?
Oh, so that's the minimum. That's the
light that has reached us.
Yeah.
Right?
It's pretty intense.
So whatever is out there, that light hasn't reached us yet. So we'll just have to wait to see.
Is that we can't measure it, or the light probably hasn't reached us yet?
The light hasn't reached us yet.
Okay, so it's not telescope limited or anything like that.
Well, I mean, you run into that problem too. I mean, you need very, very powerful telescopes in every wavelength range to be able to collect all that information from these from the early days. So that's actually cosmic background radiation that you would look at to get a baby picture, if you will, of the universe.
That's a fun one. I haven't had an astrophysicist on since the Allen Webb telescope became live. I had David Collins on right before. Yeah, it's been a while. So Maya Murphy will be on in the spring.
Oh, nice. So you will have a lot of answers to James Webb telescope questions. I've seen the news, but that's where my knowledge ends. And I know a few Dutch physicists, astrophysicists were involved in some of it, and some of whom I know personally because I went to school where they are at. So
you remember the warp on this level?
No.
Do you want to know where it is, or you just want to go?
You can tell me if I ever make it past this first bit.
It's a non-trivial jump.
No, yeah.
Steve's opening with the big questions. How big is the universe? Which is fun.
Yes, it is fun.
It's one of the things I love about the stream, that we have the range from quantum mechanics to astrophysics and everything in between. So you get a little bit of all of it.
Something about here, if I go far enough, maybe I'll get stuck in there.
I don't.
Maybe I got a little bit. I don't know if this was it, but this is a thing.
Yeah. So the vine is in that one. Nope, you're beyond it.
Oh, which ones?
Too late. You're gone.
Okay, well, I'm going then.
Yeah. I'm impressed you remember the first warp.
Just gonna avoid all these nasty plants that are gonna eat me.
That's a veteran move. All right, if anyone has questions for Dr. Christianne Beekman, she's happy to answer them. She's an expert in condensed matter physics, things like pulsed laser deposition, magneto-optic materials, 2D materials, frustrated magnets. She is happy to answer questions on any of those things. We're starting strong with request a factoid. Scuzzbot Wotus wants their mind broken by a factoid. What knowledge do you want to drop on them?
Well, let's start with the one that I started with saying in my little intro. Can magnets be frustrated?
Oh, Reese's Pieces just dropped the exact same question in, so we'll go with that. What are frustrated magnets?
So, frustrated magnets are materials where the atoms, right, they're arranged in nice, ordered, what we call lattice structures. So with nicely arranged spacings and distances with respect to one another. And so according to their distances, if these atoms are magnetic, so if a little magnetic dipole on each of them, then they're going to want to align themselves in a particular way. So usually that means all pointing in the same direction. That's nice. That's called a ferromagnet, by the way, which is by no means frustrated. If they all want to point anti-parallel, there's little dipole magnets, then it's also not frustrated. But that's sometimes easy to do when the material has a square or cubic shape to it. But if the crystal has atoms that are arranged in a triangular pattern, now the system can satisfy lowering its energy as much as possible according to this magnetic interactions between these atoms. And so the geometry of the material itself prevents it from finding what we call a ground state. And so that means it has many, many possible states available to it at even extremely low temperatures. So otherwise stated, it has a lot of entropy, if anybody on there knows what that means. So just many, many possible microstates available to it. And that's interesting. At least I think it's interesting.
That's all that matters.
Isn't it? Really?
To drive your research forward, yeah.
Well, at least I have to find it interesting too.
Yeah.
To keep working on it.
Yeah.
So I'm interested in these materials because they'll do funny things at low temperature sometimes when you give them external perturbation. So they don't really want to order, what we call order, by themselves. But if you nudge them in the right way, then you get all kinds of emergent physical properties that you perhaps find in thin films that we make by confining the material, but not find in what we call a bulk sample. So I like to frustrate things further, if you will, by putting it under strain or stress, by distorting the crystal in any which way I can, and then figuring out what's happening to those properties.
So the key to frustrated magnets, if I heard that correctly, you have parallel and anti-parallel if there's even numbers. If you have a triad of them, it starts to go crazy because it
doesn't know what it wants to do.
Huh. It's that simple.
It is pretty much that simple.
There's obviously complexities on top of that, but it's just, 3 is not as balanced out as 2. So that makes sense.
So it can't satisfy I can't get past this.
So a fun factoid about Mario: if you let go of the jump button and you run into a guy, you'll actually kill them.
Really?
So even if you're under them, as long as you're not holding the jump button anymore, it'll actually think you're on top of them. So if you let go of that button when you jump into them, chances are you're going to kill them.
Okay.
Which is kind of
good to know. But I never knew that fact, or I knew it once and have long since forgotten it. Or that.
Oh, veteran. Nice.
I suddenly saw the bullet. I'm like, I can use that.
Cuddle Puppy says, frustrated magnets are magnets who have heard the Insane Clown Posse song. Have you heard that song?
No. I apologize, but I don't know.
No, you don't know. I mean, I'll send it to you. I sent it to Ryan Bombach as well. But there's a song called Miracles by them, and there's a line, something along the lines of, magnets, how do they work? Like, that's literally one of the lines in the song. So, yeah.
Okay.
3 Sharon 3, dipoles, at least I know that word. Maybe this is one of my students. We covered dipoles fairly recently in class, talking about polar versus non-polar molecules, whether they have a dipole moment. Yes, dipoles are universal. Physics, chemistry, engineering, materials science, we all deal with dipoles. So,
we have the same problems, physical problems, but sometimes slightly different language, I find, between physicists and chemists. But
and different lenses to look at the problem.
Yes, absolutely.
Yeah, but you've worked with a number of chemists. Like we're both in the material science and engineering program, correct. So we bridge those boundaries. Hammer Brothers. Unforgiving Mario characters.
But I'm already in world 5.
Yeah, no, you're making progress. I'm impressed.
I probably should not have taken the shortcuts, means it's harder now, but that's all right.
No worries. Infinite lives. And we can also put in a code where you always stay big if you want. That might be too easy, but who knows?
That might be too easy, yeah. Can't make it too easy on me.
The challenge is fun. That's one of the things I like about the original Mario games. Like, modern games have an easy setting. None of these do. But yeah, if anyone has questions for Christianne, she's happy to answer them. Talking about frustrated magnets and dipole moments. Do they have dipole moments in astrophysics? They talk about it?
I'm sure they do have. I mean, any magnetic material has poles, right? Has a dipole. Either macroscopic or, on every atom. But, I mean, a neutron star has a large magnetic field, right? So it has poles. So it's a dipole in itself, I would say. Right? As is our planet, right? Earth has a dipole moment, too. It's a magnetic field.
So I don't know if we answered... kind of mixed up our questions with our factoids. I'm going to do a quick factoid for you, Scuzzbot. This is one Mario related. So the entire game of Mario is 32 kilobytes.
Really?
Is how big this game is on the original 8-bit cartridge. And so we do a screenshot for our YouTube video for Ask a Scientist Gaming. And so it's a screenshot with the title screen plus me and Christianne on the green screen overlay. And that file is 390 kilobytes.
Okay.
So it is more than 10 times larger than the game we're actually playing right now.
That's crazy.
Yeah. When you think about it, it's so impressive how much information they packed into this game.
Absolutely.
It's absolutely amazing. All right. So we'll start with the history question. I mean, you've done research in a lot of different countries. The question is like 6-year-old you was probably not, I'm going to be a condensed matter physicist. At some point you transitioned into this area of interest. What was that journey? What brought you to where you are today?
I would say that, well, I mean, I had no idea what I wanted, just to be totally honest. I probably wanted to be a vet still when I was 6 or something like that.
Yeah.
Doesn't every kid want to be a veterinarian at some point, or a doctor or something, right? But I really, actually, my physics interest peaked in high school because I just had a fantastic physics teacher. So I think that helped a lot.
It's surprising how often that's the case. Just one good teacher.
Yeah, one good teacher, and then I started, looking into it a bit more, and then I was like, okay, I need to go to, or I want to go to college. What am I going to do? And I looked at many things, including like a law and I don't know, lots of things. Fun fact: my identical twin sister is a lawyer, so we, so yeah. But then I just looked at a physics program. I was like, okay, this is a very versatile program that will get me, a lot of good knowledge and applicable knowledge. Probably a job, right? So some of it was practical. And then I decided, why not do that? And so I liked it. I stayed with it, and I got my master's degree, and then I was like, okay, let's do a PhD. So it wasn't as well planned, perhaps, as others may plan their journeys, but yeah, no, I loved it every step of the way. So, but it was essentially just sort of taking one step at a time kind of journey. And yeah, then I did a PhD and a postdoc and another postdoc and ended up here. Never thought I would end up in Tallahassee, though.
That's true for most of us. I mean, when I ask most guests that question about, the journey, you'd be surprised how often very few people know from the start. Like,
oh, yeah, I'm sure.
Brad Johnson was one of those. He does like geography and meteorology, and he was in like a hurricane when he was young, and that affected him. And that's what he studies now. So there's some of those scenarios, but most people, it's just kind of a meandering journey. Eventually find something you fall in love with, which is ultimately the goal. Any undergrads that are listening right now, and just keep doing stuff until you find something you genuinely
you'll
enjoy.
find something.
Yeah.
Everybody usually finds something at some point, and it can take a while.
Yep. It's a lot of exploration, because our lens is so limited. Just what we've experienced and what we've heard from our parents or others.
That's true, and I'm actually first generation college student.
Oh, wow.
So is my twin sister. So my parents didn't go to college. So yeah, it was a whole new thing for us, also as a family, to have two kiddos in college at the same time. And we both landed well, I think, and really still enjoy what we're doing, what we started way back when. So
that's awesome. That's Netherlands. So college was free, or
not free, a lot cheaper than
a lot cheaper than here.
Yes, a lot cheaper than here.
Yeah.
No debt at the end of it. So you just done after 5 years. A master degree was the only option then. So no, but now they have a bachelor master system, but not then.
I see.
So yeah.
I mean, that's one of those things, like, in terms of opportunities for people that, first generation or couldn't afford it, like, the U.S. is terrible for that. Either you go in debt or you don't go to college. Like, that's your two options.
True.
So, yeah, no, that's amazing. I didn't know you were first generation, which is, I don't know about the likelihood of success in the Netherlands, but in the U.S. it's significantly lower if you're first generation student, just because they don't have knowledge about how any of the system works, right? In terms of classes or registration, or even you can talk to professors, you can go to office hours. Like,
correct,
that advice is not there. So, no, that's pretty amazing. All right, back to the science. Scuzzbot Wotus wants to know, will magnetic monopoles ever be discovered?
Well, okay, it depends on who you ask, whether they already exist or not. So if you ask me, I would say monopoles sort of already exist. in certain condensed matter systems, like the ones I've been talking about, like these frustrated magnetic systems. So are there truly magnetic monopoles? I mean, you can agree to disagree on that. But it's essentially what a magnetic monopole in this sense is a dipole moment that you have somewhere in the system, and it's highly dynamic in this system because of all this energy that the system still has when it cannot order. So, and if you then go to the correct temperature, which is by no means near room temperature, and then induce an excitation in the system, it will migrate around in the system as if it's a magnetic monopole. So it will mimic a monopole, because if you flip one spin, it's going to sort of flip a chain of spins and create what you call a Dirac string. So maybe people have heard of Dirac. That's East Dirac Drive is where the Magnet Lab is. He was here for about the last 10 years of his life in Tallahassee, and he essentially invented or theorized the existence of these strings, and we now see them experimentally in these magnetic materials that I work on. And so in certain circumstances, you get an excitation that will behave as a magnetic monopole, is the short story of that.
So it's a transient, it's not a true magnetic monopole.
No.
It's a transient moment.
It's a dynamic state, but you would have on a specific triangle shape in your material, that excitation that lives there in your triad of spins, that will have a charge, a magnetic charge, if you will, of the size of a magnetic monopole. So we call it a magnetic monopole. But, other people might not, right? Because it's not a static monopole that will live in the same spot for, a long time.
So that's interesting. Is the transient useful for anything?
So those magnetic monopoles will be highly dynamic, right? And they form strings. And so you can imagine it actually as sort of a magnetic current running through the system. And so in that sense, you can measure this magnetic current flow. People have done this experimentally in these systems. So that could be useful as a sort of different information carrier type situation. But the problem is, of course, this works at, a few kelvins or even millikelvin temperatures. So that's the problem, right? Is it applicable? No. Just because of those temperatures, and you need a magnetic field, and so it's not that trivial, right? It's not like we can make these things at room temperature and use them for quantum computing or something. But as a condensed matter physicist, I would claim they, in fact, exist. Sort of. So
might be starting fights here or the YouTube comment
people can
section,
agree to disagree. That's what science is all about. So you have people that believe, most condensed matter people that work in this field believe they exist in this specific subset of materials under specific external perturbations. So
there's no standardized definition of magnetic monopole that somebody's going to claim you're right or wrong.
I think theoretically, the specific magnetic phase that they're associated with is pretty much as closest to the actual definition you can get.
I see.
Which, depending on who you ask, that can be a true definition as well, right? So it depends on who you ask, probably, right?
Yeah. I'm sure there's been a lot of perspectives and opinion pieces.
Absolutely, yes.
People saying whatever they want to say.
Yep.
There's no universal accepted thing yet.
I just published a paper in Nature Communications with monopoles in the title, so there you go.
Was there an opposition?
No. 3 referees liked it, and yeah.
It's good. At least 3 people agreed.
At least 3 of my peers agreed with the work and really liked the paper. Yeah.
That's awesome.
Yeah.
Congratulations.
Thank you.
And those are the papers that actually get cited a lot if someone wants to cite.
True. Those are the papers that get you to your next promotion, right? That sort of thing, because you need some high impact stuff.
So Scuzzbot would have said, best answer I've received to that question. Usually I get a no. The no is a less exciting answer.
Sure. I like to be a little bit controversial, perhaps, but yeah, it depends on who you ask.
I mean, so I guess we'll follow up with that. Permanent dipole or permanent monopole. Is that going to exist? Is that theoretically possible?
I mean, most people think the magnetic monopole itself is a hypothetical particle, which, in part is, I would say they do exist, but you have to be a bit careful indeed with your definitions. So I would say, a permanent monopole? Probably not. I don't think Maxwell's equations don't allow that.
Yeah.
I don't think so. A true magnetic monopole, right? That is like a magnetic dipole, completely stable and static object. I doubt it.
It's almost more exciting if Maxwell is wrong.
Yes, that would be. I mean, that would stir up
a little bit,
a little something in the physics community.
Yeah, it would break all of electromagnetics. That's fine.
We have to revise some textbooks. It's okay.
All the textbooks.
Yeah.
Literally all of them. So Scuzzbot, the answer is no on permanent. So you still got your standard answer.
Yeah. Yes.
But no, that's a fun one. Oh man, triboluminescence. We're going to optics / high energy physics. Does light travel back in time in a negative refractive index material?
That's a good question. I don't know if I have a satisfactory answer to that question.
Well, I guess we'll start with what's a negative refractive index material?
I'm not really an optics person.
Yeah, I was going to say, have you taught optics before?
Nope.
That's a very, very specific.
That's a very specific question. And I'm also going to say, considering the distraction here with playing the game, I'm probably not going to come up with a satisfactory answer to this question.
I mean, there probably isn't one for this traveling back in time and negative refractive index.
Oh, no, but the negative refractive index, I would have to think about that one even.
Yeah.
What does, do we actually have examples of materials that have a negative refractive index?
I know they've done like layered materials that behave like they have a negative refractive index. I think it's cheating, but I don't think it's necessarily
that would be cheating because all the materials you stack have a positive refractive index and they sum somehow by, bouncing stuff around probably to become something that has a net negative refractive index. But I don't know if that's the same thing. And I don't think you can travel back in time using layered material like that. But, it would be nice for somebody to prove me wrong on that statement because it would be highly intriguing.
The negative refraction Wikipedia page is pretty light, so I'm guessing there aren't a lot of examples. It looks like it's mostly a mathematical.
It's probably a hypothetical situation.
I imagine somebody so like when you look down in water, you put like if you're spear fishing and you try to hit a fish, like put the spear in the water, you can see it bend one way. Negative refractive index is where it would bend back towards you when you actually see it. So somebody has probably simulated what that's looking like. I don't know if they've actually done it or not. It's kind of crazy.
That is crazy. I've never heard of that being possible in a single material, but
I mean, it's probably another one of those that's theoretical. Which, when you work in physics, that's kind of the fun part, right?
Oh, sure. We can come up with all kinds of scenarios. If we're theoretical people, we can dream up all kinds of scenarios, whether they're, real world physical, like can you make it in the lab? That I don't, that's a second question. But sometimes theorists don't really, care about that much.
As long as the math works out.
Right. So I always like to stick close to my experimental roots. A little bit.
You're on the much more applied end of the physics world too.
Correct. I make materials. I try to arrange their atoms in such ways that, I can manipulate their magnetic properties.
Yeah. Thanks. I'll keep working on my time machine until I hear otherwise.
It's funny.
Fly fast enough through.
Cheers to that.
Refractive index. Cheers. Speaking of which, what are we drinking today?
I don't know if you can see it.
Actually, it's green screen, so you won't be able to see it. How do you pronounce this?
Eyinger.
Eyinger. Oktoberfest Marzen. This was... You asked for, what was it, a Hefeweizen or an Oktoberfest beer? This is... Brings you back to, we'll not say childhood, but back to undergrad.
No, I mean, I don't discriminate against any beer, but I do like my German beers, and Belgian beers and Dutch beers. And
that's crazy. So the other one you asked for is the Trappist beer category. Mm-hmm. So Steve Leonard, he had Chimay last.
It's also very good.
Yeah.
Which color? The blue is really very good, but it's a bit high in alcohol.
It is. It's 8%. So that was... Oh, was it red? Oh, I'm sorry.
Oh, well, that's also... I mean, all Chimays are good.
Yeah, it's like 7, 8, 9% or something. But...
I was in Belgium not that long ago and had a Chimay Blue with a very nice dinner.
Yeah.
It's fantastic.
That's fun. The same beer store, the beer... What is it? Beer Stop? Mm-hmm. On Mahan. That's where I found it, actually. But it's crazy. 2 guests in a row, and I'd never heard of this category of beer. I probably heard of it, but I never had it before. No.
Really?
No. But my first beer was in Germany, and it was a Hefeweizen, actually.
Well, you can't go wrong with that.
Yeah,
I mean,
exactly.
anybody would, if you don't like beer much, a Hefeweizen is a pretty safe.
Yeah, just very smooth, gentle. Like it influenced my taste. Now my default is Blue Moon, actually.
Oh, that's not bad either.
It's very similar.
Yeah, that's not bad either.
But Oktoberfest, that's just a class of beer, apparently.
Yes, because actually, is it Oktoberfest? Are they doing it again this year? I wonder. In Munich?
That's a good point. They shut it down for a couple of years.
Yeah, because of the pandemic. But they're probably doing it again this year. And it's soon, if not, well, probably not already.
Yeah, we can
late September.
Oktoberfest 2022. September 17th till October 3rd. In Munich.
Yeah, it's nice.
Yeah, that's exciting. Coming back. It's coming up soon, too. Oh man, I completely missed it when you beat the Congratulations. It was a battle. Mm-hmm. Is Cuddle Puppy wants to know, is Oktoberfest the place where they have the giant troughs that everyone pees into?
I have never been to Oktoberfest. Well, if everybody's drinking copious amounts of beer, there has to be a solution for, that part of it too. Not sure what they came up with, though, as a solution. I'm sure Google knows.
Yeah. So I remember being in Amsterdam. It was actually my wife and I's honeymoon. We went Amsterdam as part of the trip, and they had just stand-up urinals that didn't have sides or walls. It was just like out there on the main strip. And it's better than people peeing on the street. So
oh yeah,
I mean, I respect the commitment to the cleanliness and health of everyone.
Yes,
even though privacy is sacrificed.
Well, they want to not dirty up the streets too much.
Yeah, no, it makes perfect sense. I thought it was super convenient, but as long as you're not modest, you're doing okay. And it's easier if you're male.
Yes, definitely.
But so it goes. That's Cuddle Puppy's take home from Oktoberfest.
There you go.
Shared urinal troughs.
I want to go at some point, but of course the pandemic has, prevented that. But also, usually it's hard to travel. Yeah. Harder to travel during the semester, right? So it's really difficult to.
Yeah, I'm doing my first international conference in October, actually. Oh. I'm missing 3 days of class, which I feel a little bad about, but I mean, it's Milan, Italy.
It's part of our, that's nice.
Yeah,
part of our lives again.
Yeah. To be perfectly honest, I'm kind of glad I didn't travel for a while. I mean, especially with young daughters.
Same.
Like, it's not a vacation ever. It's
No.
stressful. It's work. That's a super first world problem thing to say, but it really is.
Correct. Yeah, it is. Almost.
So close.
Not that I was in control here, but
Oh man, we're 35 minutes in. We should do one of our predictions. Which one do you want to do?
anyone is. How about just the first one? We've been talking about magnets a lot.
Yeah. Oh, magnets are fun questions.
Oh, I love magnets. I use them all the time to measure my new materials that I make.
I'm one letter too long on them. What happened? All right, we're going to get rid of a space between magnetic and field. Hopefully you guys can translate the word. All right, ladies and gentlemen, we're going to do a prediction now. Here on Ask a Scientist Gaming, we do scientific predictions rather than gaming related. Actually, we can do both, but this one's going to be a scientific one. We're going to put a science question in there. You are on Ask a Scientist Gaming honor code. You can't use Google to look up the answer. Instead, you're going to have to use your intuition or your knowledge or factoids you may know. But the question that we are going to pop up right now is... what is the strongest human-made magnet versus the Earth's magnetic field? Is it greater than 1,000,000 times stronger or less than 1,000,000 times stronger? So this is the strongest human-made magnetic field. Is this a steady-state magnet or is this a temporary explosion magnet?
Steady state.
Mm-hmm. Okay, so we're going to ignore the magnetic field created by things like nuclear bombs. Instead, this is a steady state magnet. Is it greater than 1,000,000 times stronger or less than 1,000,000 times stronger? And if you're not following us, click the follow button, get your standard internet units, and you can gamble them on this science question. Question is, strongest human-made magnet versus Earth's magnetic field. Is it 1,000,000 times stronger or less than 1,000,000 times stronger? See, these are words like magnitudes we don't think about often.
Nope,
like
they're
size
not.
of the universe, size of the Earth, that's one thing.
Mm-hmm.
Size of fields is a very different monster entirely. It's something.
And it's something you can't see, right? I mean, how strong is your fridge magnet? And
yeah,
I mean, those are all. We have lots of magnets in our lives, but how strong are they really?
yeah. Just for our computer drives and strongest human-made magnet versus the Earth. 1,000,000 times stronger or less than 1,000,000 times stronger. You have about 45 seconds to put your guess in there, or if you know the answer, be confident, bet a whole lot of internet points on it. We'll see what the answer is. And I look forward to hearing more about this, because there is literally an entire, compendiums of people dedicated to making stronger and stronger magnets. Like, that is their job, which is kind of fun. All right, last 10 seconds. Throw your predictions in there.
I don't make them. I just use them.
Yeah, that's fair.
I'm very happy. These
kind of
magnets.
dangerous to make those big magnets.
Oh yeah.
It's a high risk endeavor.
Things do go wrong sometimes with these things.
Yeah.
Too.
All right, Christianne, what's the answer? Greater than 1,000,000 times or less than 1,000,000 times?
It is greater.
Greater than 1,000,000 times stronger. Congratulations, Reese's Pieces. So the strongest human-made magnet is greater than 1,000,000 times stronger than the Earth's magnetic field. And so the answer here, you put the actual numbers. So the strongest human-made magnet is 45 Tesla. The Earth's magnetic field is 0.0000035 Tesla. It's kind of crazy. That's 1,000,000 times stronger. I'll put the numbers in there for you guys.
So the 45 Tesla, just to give a little nuance, is the strongest magnet we have at the magnet lab, and it's what we call DC field, so it can be held for a long time, like static. But we can also, in Los Alamos, which is a sister facility to our magnet lab here, they can do pulsed magnets, and sometimes they destroy the magnet in creating this pulse that's like milliseconds long. And there they can do 100 Tesla, so it's even stronger.
So that's 100 Tesla single pulse. How long
Single
is that?
pulse, very short, right? Less than a fraction of a second.
Fraction of a second. But you can
And
get
you'll
100
just
Tesla.
you get a measurement done. It's a single shot measurement because after that your magnet is dead. It's exploded, and you either have your data or you don't. So yeah.
So you're saying Nikola Tesla was 1/45th as powerful as the world's strongest magnet? He was 1 Tesla. That's true.
Yeah, that's true. And most magnets, considered strong magnets in our lives, like a junkyard magnet or those things that lift cars, those are about 1 Tesla.
1 Tesla.
Yeah, that's sort of your average best you can do in those situations where you're talking about maybe an electromagnet. 1 Tesla is about what you can.
1 Tesla.
reasonably
You can
do.
pick up semis with that.
Yeah,
45 Tesla.
so it's a whole lot stronger.
Oh.
And we stick, our samples in there to figure out what their materials properties are once you put them in really, really extreme conditions.
So Tesla was one of the greatest scientists and as strong as a scrapyard magnet.
Yes,
If that's the factoid you remember from this, that's
pretty much. That's it. Yeah.
I like it. All right. So we had 2 questions. I missed one back here. It's what's your favorite magnet?
My favorite magnets. I collect fridge magnets, but that's a lame answer. My favorite magnet is actually the 18 Tesla magnets. There are 2 of them in what we call the millikelvin facility. It's my favorite because that's what led to my most recent many publications. It's easier to get time on it, and it will do most things that you want from a strong magnet and low temperature environment.
Yeah. Follow-up
So-
question to part 1 of that. Do you collect the fridge magnets because they're magnets or because what's on them?
Both. I actually love fridge magnets because they're so simple.
Yeah.
And they stick, on your fridge because your fridge door is a metal and you can magnetize it with the magnetic field from your little magnet that you bought.
Yeah.
But also because it contains a souvenir of, wherever I travel to, which before COVID was, lots of places.
Yeah.
Not so much now anymore. Well, we're starting again.
Yeah. I love fridge magnets, and Ryan and I were talking about this, that the invention of the U magnet that's small enough to go on a fridge magnet was actually a breakthrough. You want your logo facing outward all the time.
Yeah, exactly. So they're much more intricate in their design than you might think. Like, how they work. I mean, that type of design.
Yeah, one of my favorite things to do, and I learned this as an undergrad, I did a summer RU that was solid state chemistry. And they had an entire section of lecture on magnets, and they had this like activity kit with solid state materials. And one of the activities was literally taking 2 of those magnets and you rub them over each other, and you can actually hear the rippling because it's attractive and repulsive, and it repels each other. You can actually hear it vibrate based on.
Nice. That sounds cool.
Yeah, and like modern ones, the spacing is much smaller because I guess manufacturing has gotten better, but older ones you can actually see the rippling effect from the U magnets, which is kind of cool. Just a really fun demonstration of fields repelling and attracting. Reese's Pieces has another follow-up. How many fridge magnets do you own?
Ooh, that's a
You don't have
a
to
good
answer this
question.
if this is too personal.
Oh no, I mean, whether I know the answer is the question. My fridge is pretty full. Like I don't have a lot of real estate left, and it's like your standard American double door fridge. So, at least 50 is my careful. At least
On a single fridge?
on my single fridge, something like that.
That's pretty fun.
And they're all from different places in the world. Like
Man, we should have made a prediction about that.
Yeah, I didn't realize. I look at my fridge every day, and
Yeah.
some of them are boring stuff like my my Nespresso membership number,
In the magnet.
but it's on a magnet on my fridge because I have to remember that stuff. I need
Yeah.
to get my coffee. But most are from places I've been in Europe, Asia, wherever, U.S. destinations, all kinds of stuff. that I've collected over the last, I don't know, 10 years maybe.
All right, Triboluminescence wants to know, what's the strongest magnetic field known? E.g. like a star or something.
Oh, I mean, you have to go to astrophysical sources. Neutron stars usually have high magnetic fields. Black holes, right? All that gas swirling into them usually will have something. So, but my money would be on a really dense neutron star.
Ooh, so my Google search, new record for strongest magnetic field in the universe, more than 1.6 billion Tesla. And it is a neutron star, according to that.
It has to be, because, that's what left over after a star has collapsed. And if it was a really massive star, that neutron star really dense, small, and will rotate really fast. That will have about the largest source of magnetic fields that we know about in the universe. Unless there's objects that we haven't discovered yet. There's always that possibility.
It's probably true. That's almost always true, right? That's pretty fun. Triboluminescence. Isn't that what Thor's hammer is made from? Asking the important questions.
Oh, sure. Well, but now he has that's a new, his axe, right?
Yeah.
But his hammer probably was made at the same, I forget the name, and Marvel fans will not like it, but it's the neutron star that he brings back to life in the movie. I do love the
Peter Dinklage, whatever character he plays.
Yes, the
blacksmith.
Yes.
Forging stars.
And I forget the name.
Based on a true story.
I forget the name of both Peter Dinklage in the movie and the star that they're on.
1.6 billion.
I know, that's actually crazy. I was gonna guess in the millions, but billion, that I wouldn't have.
Here we're excited we get 100 Tesla.
Yeah, definitely. I'm excited about 45, even 20 Tesla. That's already 20 times stronger than your average junkyard magnet.
Yeah.
So
billion is now. I can't even comprehend the implications of that.
No, that's just something you can't wrap your brain around.
One of the claimants to the Iron Throne and a master blacksmith. Yes. The most ambitious crossover in Marvel history is with Game of Thrones. Absolutely.
That's funny.
Yeah, there's a really fun book called The Physics of Superheroes. I don't know if you've heard about this.
No, I haven't, but I would be interested in reading it.
It's teaching classic Newtonian physics.
Mm-hmm.
I think it does calc-based as well as, the algebra-based. But the idea is a professor from U of M, I don't remember his name, but he basically said students weren't super interested in the ball rolling down a hill, but as soon as you have, like, Spider-Man, stopping Gwen from falling and it breaking her neck, and you can calculate force, students start to care. It's not real world relevant, but it's at least interesting. So he started teaching his class based on physics problems from superheroes, basically.
I see.
How fast, like, original Superman couldn't fly, he could just jump high. So the question is, how high does he have to jump to actually get over a building? And it's just, classic physics problems, which is pretty fun. So somebody clearly needs to update that for neutron stars and 1.6 billion Tesla magnets.
Yeah, that's crazy.
So what about an explosion? Like any bomb, like a nuclear explosion, they create magnetic fields. Do you have any idea how strong those are?
Not really. No, I've never Googled it. I'll be blacklisted if they Googled it. Probably. No.
I'm going to look it up quick.
It will definitely fry circuits in a fairly large range, but I don't even know exactly what range that would be. It's a couple miles maybe, right?
Yeah, it's essentially an EMP, right?
Yeah. But how strong the pulse needs to be in terms of Teslas for that to happen. But I'm sure Google or Wikipedia or whatever knows.
There is a massive article dedicated to explosion-based EMPs.
I see. Wow. Somebody really thought about it, huh?
Well, I'm sure, like weapons and warfare, this is a genuine concern.
Oh, I'm sure it is.
How big that
it
radius is. Actually studying that. Hi, search physics on Twitch and found your stream. Can I ask any question? Absolutely, Ken. Welcome. If this is your first time here, this is Ask a Scientist Gaming. We combine mediocre gameplay with expert science. I'm Ken Hansen. I'm a chemist. I do photo-driven chemistry. But joining me today is Dr. Christianne Beekman. She is an expert in magnetic materials, optomagnetics, pulse laser deposition, frustrated magnets. She is happy to answer any questions you have on those, as well as anything else. She also teaches astrophysics, which is kind of fun. You done no particle physics yet?
Nope, not yet. I hope to stick more with condensed matter, though.
What is your favorite Zimbabwean dish? Rice dish?
I don't know if I've ever had a Zimbabwean rice dish, but I can tell you I love Indonesian rice dishes.
That's fun.
Indonesian cuisine is fantastic.
Yeah.
So flavorful. But I wouldn't know about... and Ethiopian food is delicious, but I don't know how different that would be from Zimbabwean.
Yeah.
Because I've never had Zimbabwean food,
That's
as far
fair.
as I know.
Ask
If anybody knows about this, an African restaurant in Tallahassee, please let us know. I would love to go eat there.
Good question. Have you found any? I
Nope.
can't even think
Nope,
of any off the top
nope,
of my head. That's a really good point. Frozen Space, getting back to your question. Welcome to the stream. First time chatting. Thank you for joining us. Will we run out of natural magnets eventually? And if so, can we make more human-made?
That's an excellent question. And right now, you're already seeing that people are starting to move away from what we call rare earth magnets because, will we run out? Maybe not, but they're not easy to mine, and they're also not that abundant. So the prices of those things, those raw materials, are quite high. Mm-hmm. So well before we actually run out, I think the supply chain issues that we're already experiencing for many products will become significant for these magnets that we have come to, rely on, especially for permanent magnet materials. So yeah, if you make thin films, you can sometimes, if you stick the correct materials together, create magnetism at an interface between two non-magnetic materials, for example. So it's among the things that scientists like myself are doing. And now, if you don't need those magnetic materials, but you can still potentially create the magnetism that you would need, say, for a hard drive, or they won't be strong magnets, but there might be enough for magnetic memory applications, right?
So what's the go-to element? It's neodymium for a lot of the statics, right? That's and it's just because it has 7 unpaired electrons.
Correct. So neodymium is one of the ones. Yep.
Yeah.
But it's pretty expensive.
Yeah, and getting increasingly rare.
Yep. Yeah. So that's definitely is a problem of the future.
I mean, imminent future too.
Yes.
It's
well, we're already seeing the problems with some of these things. Any suggestions how to get past this dude here?
I get inside his hammer arc.
No.
Then you can go under him. Fun factoid on Bowser. So on Mario, it can only process 6 sprites, like 6 objects. So if there's a fireball, him, you, and 8 hammers on the screen, 5 of those hammers don't actually exist with the hitbox. So they show up on the screen, but they can't hurt you.
Yeah, but how do you know which one it is out of those?
It's basically the first 3 or whatever have actual hitboxes. The other 5 are transparent, so you can jump through them. So
wow. Okay, I will try to remember that.
It doesn't matter.
But also applying that, thinking about that and applying the motory skills is, you can see it is not so easy.
Well, it's important for the speedrunners because, when you get to Bowser at the end, you have to get to the axe right away. So either you go under him or he throws hammers, and you have to know when to jump through them.
Maybe that's the key. Yeah. Just keep running and don't think about it too much.
That's what I do. By the way, do you know what the world record in this game is?
No.
You want to throw a guess out there?
Total completion time?
Yep, with warps.
Couple minutes?
That's a good guess. It's 4 minutes and 54 seconds. And they are the latest world record is 3 frames away from perfect Mario gameplay, which is kind of crazy.
That is crazy.
Yeah, like it's basically computer quality execution for 5 minutes straight.
Yeah. Wow.
36 years later, we're pretty good at playing Mario, is what we've learned. Cuddle Puppy is upset.
Except me, I'm stuck at this point. For what, 20 minutes now?
In your defense, you haven't played this in 20 years.
No,
we can
that's
switch
good.
to another game. You're not stuck with Mario. Whatever you want to do, we can change it up. So we can go to Herbie or Tyson's Punch-Out, Dr. Mario, any of the other Marios, Tetris. What do you want to do?
Let's punch some dudes.
Let's do Punch-Out. Cheats are loaded, but they're not active right now, so you're on your own. Cuddle Puppy is upset you didn't answer the Zimbabwean food question. They want to go to Ask a Zimbabwean Chef Gaming. Sorry, we don't deliver on food choices here. All right, 82 Cubes wants to know. I've heard of laser cooling, but it looks like a laser should be hot. How does laser cooling work?
So, so that's really an atomic physics optics question. We try to get started and then try to make my brain work at the same time.
It's okay, it's class joke.
So essentially the laser cooling works that you put the atoms in a very specific location and the laser keeps them there, so to speak. I don't know if that makes sense. So you're actually creating a atomic lattice using that laser, and the potential of that laser, right? That potential landscape, so to speak, that the laser creates will create your lattice. So then you can keep your atoms really still, and that is equivalent to a low temperature, essentially, because atoms like to move around.
I mean, that's a really... It's a fun technique because it harkens to something I talked about in class where, you know, temperature is just kinetic motion of atoms.
Exactly.
Right?
And
Like
if you keep them still in whatever way, which that's optically or in any other way, if you can keep them still, you can avoid them doing this wiggly motion. Then you're essentially reducing the temperature. However you accomplish that doesn't matter, but the effective temperature of your system is going to come down if you can, you know, stop your atoms from moving.
Yeah, I should bring that up in class, because when people think about cooling stuff, it's like put it in a fridge and steal the heat out of it, which is one way to think about it, but arresting motion is cooling, like stopping motion.
Correct. And that's what they do with that technique. I do the opposite. I shoot a laser at a material and it will make it really warm, effectively evaporating it. It's not exactly the same as evaporation because the thermodynamics are a little bit different, but it can be sort of thought of as analogous to just thermal evaporation, but through a laser pulse. So.
And fun factoid on lasers is the laser beam itself is not actually hot at all. It's only when you absorb those photons and convert them into heat.
Correct.
So you're taking that laser energy, photon energy, turning it into vibrations, and those vibration motions are what create the heat and burn your hand and whatever it is. But
correct.
Yeah, laser itself, if it's not absorbing, it's fine. It won't do anything. Wouldn't recommend putting your hand or eye in a laser, but you get the idea.
Definitely don't do that. Because again, the laser hits your hand or something, and atoms start to move more vigorously. So things get damaged in there. So that's really all it is. Kinetic energy of your system.
And that's interesting. Maybe you don't know the answer to this, but I'll ask anyway. It says, how do they measure the atomic motion in it being frozen?
How do they measure the atomic motion?
You have to view the atom in the laser field. I guess maybe you see it in the laser coming out the other end, and how that's...
Well, I mean, my guess is, I mean, you would do some... I don't know the answer to that specifically. But how do you get atomic positions? That's not so easy, right? You can do an indirect technique like diffraction, right? But that won't give you really your atomic motion.
I don't remember what this guy's name is. I missed it.
I missed it too. I was trying to think about the question.
Yeah, no, we're focusing on
And I
science
couldn't
right
read
now.
that at the same time. So how do you, I mean, you could, people can do, an optical microscope and you can see Brownian motion of like silicon particle, nanoparticles and stuff. It's really interesting. So you can see that.
Yeah.
So any microscope that has atomic precision could do it, but an atomic lattice like that, that's difficult to do.
Yeah.
So how would you measure temperature? Could you do that through some kind of method, since you already have that laser? I don't know. I have to think about that. It's a good question.
I mean, there's an answer. We have
There's an
worked in this
answer.
area. We
Yeah.
just have to find it. No, that's a very fun question. Laser cooling.
But you have to be able to tell if, I mean, you wouldn't do that with the conventional thermometer. So,
No, I'd assume you'd have to actually measure the motion, or indirectly or directly.
or indirectly know what it is by knowing what the potential, right? If you know what your potential energy landscape looks
there
like.
it is. The TKO. Well done.
Yay.
3 knockouts in a single round. All right. Reese's Pieces has requested take a drink. Christianne, cheers. Thank you for joining me. She's one of the other lunatics that said yes to this endeavor. I email people and say, do you want to play video games and talk science? And she said, yes, thank you.
Sure,
That she
I
can
know.
join us. And, thank you all for joining us as well on a Wednesday night. Hopefully I have a drink in hand watching Christianne play against Piston Honda.
Piston. Okay. Let's see what this dude does.
We didn't write the game. This is the way the game existed originally. But Reese's Pieces, thank you as always for joining us. We appreciate swinging by, asking questions, particularly about magnetic materials and pulse laser deposition, all sorts of stuff. And one of the standards we like to ask, and this is relevant because you work with low temperatures, high magnetic fields, what's the biggest mistake or accident you've seen in lab?
Oh,
Either you caused it or somebody around you caused it. Proximity lab-wise.
I guess a failure of equipment is not necessarily like a mistake or anything, but it happens.
Yeah.
And so when I was a grad student, there was this, we have what we call a PPMS, which is physical measurement property system. And it also sets a magnetic field of about, what was that thing? 9 Tesla.
Mildly
So
related,
already-
before I forget, chemistry is getting one of those, actually. Mike just
Really?
got an MRI for a PPMS. Yeah.
That's nice.
Yeah.
Since
It's-
all the PPMSs are currently broken
Yes,
at the
gonna
Mag Lab,
replace
maybe
this
I
with-
can swing by and use it sometime. PPMS?
it's PPMS, right? It's
PPMS.
Physical Property Measurement System.
Yes, it's an acronym, sorry.
Yeah. But anyway, sorry, the PPMS 9 Tesla.
Yes. So yeah, we tried to set a field on that once, right? Everything was fine the day before, and now we're trying to do a measurement. I was probably trying to run it, and we set a field of, first step in a field sweep. So it's like 500 Gauss. So something, still quite a bit larger than the Earth's magnetic field, okay, but not a large field by any means. And a cloud appears above the system in the room. Essentially, liquid helium is evaporating so quickly now because it's at the boiling temperature. So as soon as you introduce any heat to this liquid helium, which keeps your superconducting magnet
Nice head.
cold, right? You start evaporating all the helium, right? So it goes from a liquid to a gas. That's a big problem because that will, be a lot larger volume. So yeah, it wants to go somewhere. And that means it goes out of the system sort of in a somewhat explosive manner. So wherever your, weakest point is, like overpressure valves that you have, that are usually connected to a recovery with like plastic tubing. So all of the plastic tubing just froze and exploded and shredded and just ended up across the room. And we all just ran out because you don't want to be in a room filled with helium gas. Right? That's
And you saw the cloud form. You saw
Yes.
oh my God.
Yeah, so we ran because it's the only thing you can do at that time. And then you later come back to it when it's safe and figure out what went wrong. And it took me, so I was responsible for trying to troubleshoot that system. It took me probably about 3 months to figure it out. What it was a cracked soldering contact on one of the plugs on the power supply.
And that was it.
That was it. But finding that is not easy because
Yeah.
every time you turn the magnet on, any current to the supply would quench the magnets. So
That's brutal.
yeah, that's probably also the time-wise was definitely expensive, but we had to ship the power supply back and nobody couldn't find anything wrong. It was a freaking crack in the solder. So the contact wasn't completely broken, but occasionally it would be, have enough of a voltage drop that it would mess us up. Yeah.
For anyone interested in grad school, experimental grad school, you are a plumber, an electrician.
Yes, everything at the same time.
Just
Yes.
Imagine all of it. You have to troubleshoot all of it. I mean, there's help, obviously. But,
Yes.
I mean, the thought of sending back any piece of equipment, one, it's expensive. Two, it takes a lot of time.
Yep,
So you
which
fix
is,
it yourself. Yeah. It's devastating. Right? Losing any period of time it's brutal in research. Cuddle Puppy, I talk about PP mass, but only on Grindr. Thank you, Cuddle Puppy, adding the important points. PP mass, you could measure it in a PPMS if you want to know the fields involved. That's a whole different experiment. Critical Ninja wants to know, do you think we could use or manipulate electromagnetic forces to simulate sci-fi like The Force? So, like, is there a future where I can extend my hand and have a sprite can catapult across the room and into my head? A sprite can catapult across the room.
Telekinesis, huh?
Yeah.
So then you have to, let's say you can surgically build in like a magnet into your hand or somehow, right? Let's think about that for a second, okay?
So you got to have a directed field.
Now I have some kind of field. It's not very directional because just, the field lines will do their usual thing unless we figure out how to, well, if you make a really sharp point, right, you can, or a tip where this magnetic field comes out, then you can really focus it, right? You can focus the field lines, that's doable. But the problem with any magnetic field is it drops off so fast, right? Its strength. So the chances you can create enough field at a reasonable distance of meters, right, or yards or whatever unit you want to use, and be able to move something that, is not magnetic perhaps by itself, but can be magnetized. That's tricky because of that very nice inverse square law that we have.
It is a squared relationship.
Yes. So magnetic field strength drops off tremendously fast with distance. So that would make that difficult over any, substantial distance. So
the 45 Tesla magnet, is that shielded or it's unshielded?
It's it's inside, a system, so there's obviously going to be a little bit of what's the thing here again? Yeah, it's obviously inside a metal system, right? So it's going to be
some degree of shielding.
But also not much, because you don't want any magnetized material near your big magnets, and it drops up so fast anyway. So we have these 10 Gauss lines or 5 Gauss lines painted on the floor near
How far away is that?
That's not that far, actually. I mean, they do close off part of that section.
I see.
So you probably don't want to bring your credit card in too close, but it's still, only several meters. It's not that far.
So Critical Ninja, the answer is if you want to wave your hand and wipe your credit card, maybe you could do that at a close distance, but you're not moving it.
You can't move a can, probably.
At least not with the magnetic field.
No, not with the magnetic field. I mean, inverse square law it's everywhere, right? Yeah. Astrophysics has it too. Light emanating from the flux emanating from a star that also drops off. with inverse square. So yeah, that's just how it is. We can't, unless somebody proves us wrong at some point. It's a pretty fundamental law, though, that I think has been well established. So
somebody needs to do a realistic version of X-Men with Magneto, where he's super dangerous within about 2 feet, but anything outside of that, he's just kind of a nerd. Can't really do anything. King Hippo.
yeah, I forget what this deal is. Oh, I need to hit him when he does his hand up.
Yeah.
This one.
Only dangerous within arm's length, yeah. And if you have magnets or higher ferromagnetic material in your body. So that was interesting. And I don't remember which X-Men movie it was. I don't know if you're familiar with those, but someone injected, it was one of the security guards, they injected like iron nanoparticles or something.
Oh,
and
yeah.
Magneto extracted them. How realistic is something like that?
I mean, we all have iron in our blood, and you can certainly make it more concentrated. You know, whether that would then be a high enough concentration that it would do anything in a magnetic field. I think, you know, when you have a surgical implant, for example, which is a solid piece of metal, if it has enough paramagnetic impurities, you know, you probably don't want to sit next to 45 Tesla. It might cause you some pain. So yeah, technically, I guess it's not impossible that you, given a high enough concentration, that you would experience at least magnetized blood, right? But whether that's actually a problem health-wise, I don't know.
That's a good question. I mean, the amount of like particles you'd have to have in your blood to make that would probably kill you anyway. So
yeah, I would think so. I think it's very nice that you.
I guess so. The follow-up to that is one of our standard questions on Ask a Scientist Gaming, and we talk a lot about movies and TV shows. The question is, what movie or TV show gets your discipline or expertise or area right, and what gets it wrong? Magneto got it wrong because he didn't follow 1 over x squared.
No, he lifts things like super far away on the other side of the globe, right? He's in where is it, Auschwitz, and stuff is happening in San Francisco or something like that.
Yep. So he's got maybe his superpower is getting rid of that dependence. Maybe it's, you know, magnetic fields don't have distance dependence in his superpower. Who knows?
But the question was about the movie or TV show, right?
Yep. Right or wrong?
Actually, I do enjoy watching this movie. What, you know, if it's, I'm not the type of person that even if it's wrong, I get too upset about it. But it's Fast and Furious. I think it's the 9th one. the magnet thing in the car. Have you seen it?
I've seen all the Fast and Furious, and I don't remember.
They have what I think is an electromagnet, and they turn it off and on, and like essentially move cars, like destroy cars and whatnot. It's crazy. And then they not just only attract the cars, right, or the SUVs to their car, right, but then also pop them back off, like throw them back off when they reverse polarity of the field. But that's all just, you know.
If anyone wants to see the YouTube clip, here it is.
Yes. That's crazy because, you know, assuming all those cars that are driving around are
the best,
are paramagnetic.
It lifts a car and moves
I know.
Like 40 feet.
Yeah, exactly. So, you know, but there's an even later one, I think, when they're you know, doing a road racing these other cars, and then they attract them and throw them back off. It's hard to describe. You should watch the clip, but it's a fun. I mean, it's an action-packed movie. I mean, I enjoyed watching that.
Christianne recommends the movie Fast and Furious 9.
Even though it's highly inaccurate, so you know, it's
suspend belief and you'll enjoy it. All right, critical Nina follow-up. What about Breaking Bad, where they destroy an evidence room through the wall? with a magnet.
Is that with the magnet? I don't remember that, but I love Breaking Bad too.
Yeah,
But I don't quite remember that scene. But yeah, no, through a wall, definitely not.
If you made it strong enough, right? You can wipe a hard drive on the other side.
I guess you could, but again, inverse square law, and you have to know that the computer is right outside that wall, and it would have to be, yeah.
Would have been fun to have like Mythbusters out at the Mag Lab.
Oh,
Just
yeah,
set up a
totally.
wall and a hard drive and see if you can wipe it on the other side. I mean, you could do the math and figure out the answer ahead of time, but to
Yes.
logistically do it is very different. Breaking Bad, Fast and Furious 9. I was not expecting that answer. I really appreciate. Yeah, I didn't. I mean, when you think about the exponential distance dependence, it's just absurd. Anything over several feet is just outrageous.
Yeah,
So,
it's just,
but all the other physics in Fast and the Furious are fine. It's perfect.
yeah, that was the one that stood out because it was magnets.
Yeah.
You know, most things aren't accurate in movies.
I heard the best summary of Fast and the Furious. It's like a cartoon for adults, right? Like it's just absurd, like dropping anvils on people and running into walls, whatever. It's a good getaway. I like it. Is there one that gets it right? The magnetic field is central. I mean,
I don't know about
several-
magnetic field.
There's
That's
several
very
disaster movies
specific.
where like the core of the Earth is flipping and the field is gonna screw up. I don't know.
Well, I mean, the magnetic field of the Earth can definitely flip. It has done so in the past. There's records and geological information on that, but you know, and it probably will flip again at some point in time. Just the question is when, and how disastrous will that be? You know, hard to say, but yeah, it can definitely flip. So, you know, but then our North Pole and South Pole will be somewhere else. Okay, so we'll adjust to that, but probably it will affect some weather patterns and whatnot. Oh, I forgot to get up.
No worries. And let me know if at any point you want to switch games. Do you want to do another prediction?
Sure.
What do you want to do?
Maybe the one about magnetic poles, since we've been talking about magnets so much anyway.
All right, we're going to throw another prediction up there. Get your internet points ready. If you're not following, click the follow button. That'll give you more points to gamble on this question because it's super important to your pride. But the points aren't useful for anything outside of the stream. But you can request a factoid and make us drink alcohol. We're happy to do any of those things. The question is, opposite magnetic poles, do they attract or do they repel? So north-south, is north-south the accepted nomenclature? Or is it,
Yes.
That's it.
Yep.
What's the origin of that?
No, that's a great question. I guess
Just
maybe
based on
because of the Earth, I would say that, right? I mean, a compass, needles. I mean, why not? I would guess that we knew about compass needles before we probably knew really about permanent magnets. But I would have to look in the history books to know if that's really
I mean, it
true.
makes sense. It would just be like, is it attracted to it? Is it repelled? Which is the nature of this question. Opposite magnetic poles, do they attract or do they repel? You are on Ask a Scientist Gaming honor code, so don't Google the answer. Instead, answer it based on what you know. And the answer is it does one or the other thing. Health is low.
I know.
Oh,
I thought it was.
But
it loses a little bit every time.
Yeah, it just chips away.
Yeah. I'm looking a little rough against this dude. I have an eye closed.
It's attention to detail. I really appreciate that. So, do you want to trick with this guy?
I think I know it. Maybe. No, tell me. Yeah. What is it? I mean, it's
So
not.
when he crouches down to do the uppercut, well, this you have to get through this.
Yeah.
When he crouches down to do the uppercut, if you just do a low punch on the side that he's on, it'll hit him in the stomach and he'll get a star out of it.
I've done that once earlier by accident, I think.
Yeah, and you can do it like over and over again. So the only other person to play Punch-Out on stream was Mike Roper from Chemistry. And I think he made it to this guy and no further. So you have a chance to be the...
I think I'll be able to. It's not this again. This is annoying.
It's the time sink. Oh man, we ran out of time. All right. Christianne, what's the answer? Do they attract or do they repel? Opposite magnetic poles.
How did they do?
Well, what's the answer?
Sorry, attract.
They attract.
Opposites attract.
Opposites attract with both electric charge and magnetic fields. The answer is most people got it right with attract. 2 people with betting 210 internet points and 1 oppositional bet. Cuddle Puppy taking the cynical view. Would have been a 22-to-1 payout, but the answer is they attract. So yeah, somebody discovered metal when in the Earth's magnetic field attracts. Going to the 3rd round. Like it.
Oh, he has a little thing on his face too.
You're looking pretty rough too. Poor little Mac.
I have 2 eyes closed.
Select or something. Somebody can correct me if I'm wrong. If you hold select during the break period, it refreshes your health or something like that.
No, I just have to pay more attention.
Yeah.
Get the timing more right here, because this is the issue. Not this again.
And we detoured on our biggest mistake in lab. So how expensive was that mistake?
Well, everything was cheaper then, so I don't remember. But shipping the power supply back, getting a new power supply, and just in terms of time. So yeah, whatever, we're talking probably several thousand.
Expensive toys.
Yeah.
So you haven't seen anything. I mean, I guess you're involved with the Mag Lab. We had somebody die several years ago.
Correct.
And that was not related to the stuff you do. That's
I don't think I can get up. No.
Magic guy. He's tough.
I'm sure I can beat him.
Oh no! By all means, let's commit to it. let's commit to the win.
Oh no! I need to go back to him now, I guess, because I knocked out. Take care of him again.
All right, so we're 1 hour and 20 minutes in. Anyone just joining us, Ask a Scientist Gaming, mediocre gameplay, expert science, playing a little Mike Tyson's Punch-Out with Christianne Beekman. She's an expert in pulse layer deposition, 2D materials, frustrated magnets, low temperature, high magnetic field measurements. She's happy to answer questions on any of that, and even the occasional astrophysics question, because we've had several of those tonight. Or about Fast and the Furious. we will journey wherever you guys want to go. Throw your questions in chat. We are happy to answer them. I mean, so just a general science experience. I mean, you're a first-gen college student, so every milestone, getting your degree, getting your PhD was obviously impactful. What's the most like I made it moment for you?
Graduating my first PhD student, I would say.
You have academic lineage.
Yeah.
Your academic child.
I mean, that's amazing. Being able to educate the next generation and getting them to their PhD is I think, one of the main reasons why I'm doing this. Yeah.
So does physics have a academic family tree website?
Not sure. Depends on what you mean, I guess, by that.
I'll show you. This is...
Not seen any, but I would be interested in it if it exists.
So chemistry has this, and I'm going to show you guys my academic tree. I'm ecstatic this thing exists.
I would be so good. I don't know. That sounds really interesting because, I've, in the meantime, graduated 3 students, so...
So here's... I think you can pause Punch-Out if I'm not mistaken.
I just pressed start and it didn't do anything. So.
Maybe I'm wrong. Actually, I can bring this up on screen if I open Explorer. I'll wait for you to take on.
Oh, wow. That's intricate.
Yeah. After this round, I'll bring it up on the stream. Critical Ninja wants us to take a drink, so we'll again wait till the round is over. Cheers. I guess you just have the whole block on this part.
No, failed. Multitasking.
Oh, you tried. It was worth it.
Almost got it though.
Yeah, remember hold select now, the left button. All right, so if you guys haven't seen this before, chemistry has this really cool academic lineage tree, basically. So you can see here all the different ancestry. So there I am, and then I have Thomas J. Meyer on one side and Mark Thompson, my graduate and postdoc advisor. And then you go back to, I mean, we get back into physics here, right? And things like Gilbert Lewis, Fritz Haber, chemists. Yeah. And it's really cool, the bookkeeping that they've done with this. Which is pretty amazing. Max Born. So that goes into the physics tree. Apparently I have no idea who made this website, but I get to add my academic kids every time they graduate.
That is crazy. That would be very interesting. Yeah.
Yeah, I'll look if there's a physics one. That's pretty fun. I think there is, but I don't know.
Somebody's asking, but where is the inventor of science?
L. Ron Hubbard did not invent science. Oh, Cuddle Puppy. Cuddle Puppy is our the troll of our stream.
Nice.
They have filled a role that we need in this stream. Particularly with, is Pluto a planet? If no, which Burger King parking lot would you like to fight me in? Interesting choice on Burger King. The math family goes back to the Middle Ages.
Oh, wow.
That's
cool crazy.
That exists. I'm going to look up and see if there's one for physics. Yeah, physics tree.
So, but you have to input that yourself.
Somebody has to. Who's your graduate advisor?
Jan Arts. He's from the Netherlands. I doubt he does that stuff, though. Doesn't,
ARTS? How do you spell it?
AARTS.
AARTS. From Leiden?
Yes, correct. I did my PhD there.
Yeah. There you go.
Oh, well.
So you could add yourself on this.
All right.
Christopher Bell?
Yeah, I know him. He was there. We had overlap.
There's no attachment beyond that, but yeah, you can find your postdoc there as well.
Yeah. Cool.
Reese's Pieces. It flagged you for posting a link. I apologize. If you can message me the link, I don't know. Our Nightbot is really touchy about links, even if you're an approved submitter.
Yay!
For some reason. Oh, you did it.
I did it.
Congratulations.
I finally found my little groove here.
Next time you see Mike Roper, tell him you beat him. He went down hard against the Magic Eye.
It took me a few tries, but... Ooh, a title bout.
Yeah, Reese's Pieces, I apologize that you got blackballed for that. But yeah, you should definitely look it up. Add your name.
We talked about him.
Does the charge. Yeah, it's pretty easy. You just do a login and you can add your names and ancestry and tie them all together.
Interesting.
Just got a message. Oh, there's the math tree. That's fun. Going back to the Middle Ages.
That is just crazy that it's going back to the Middle Ages.
Yeah. I just want to look. Like, this goes back to Euler and...
Oh, well, sure. Yeah.
Struggling to open it. North Dakota State University is what I assume is the host of it. That's pretty cool. David Hilbert. Yep, there's Euler, Laplace.
Of course, they all have to be there.
Lipschitz, yeah. The oldest ones don't even have the title of PhD because it didn't exist yet. That is real cool.
That is crazy. When was the PhD title invented now, I wonder?
It's got to be at least 1,000 years old, from what I remember.
Oh, I'm sure it is.
Philosophy.
Wow.
Middle Ages. Oh, you got it.
I know.
Golf hole. Taking the win.
Two punches at the right time. That's all it took.
Doctor of Law, Doctor of Medicine, at least the Middle Ages, late Middle Ages is how long back it goes. And
That's
pretty
crazy.
cool. I mean, that's one of the like, I am not for tradition for the sake of tradition. I'm actively opposed to tradition because it exists for the sake of existing. But one I really, really respect is the hooding ceremony for PhDs, because that is like an ancestral passing of the torch, right? I was hooded by my advisor, was hooded by their advisor, so on and so forth, going back 1,000 years to the original PhDs. And that's why I like that academic tree so much. It's just, I email my students right after the hooding ceremony, like, look, you're now on the tree. Congratulations, good or bad. You're the academic great-great-grandchild of the father of modern chemical warfare. That's how it goes.
That's funny. Yeah, I've actually never done a hooting ceremony despite doing
Oh, really?
all day. All my 3 students graduated during
Oh,
COVID.
during COVID, that sucks.
So they didn't do that. So that's the one thing that is really, well, not a regret because it's just how it is. But
yeah.
like I was quite disappointed that when my first student graduated and then the next 2 that there was no holding ceremony.
Yeah, no, I feel for you because that.
So yeah, that's a milestone I still have to experience. I would love to experience it, but I'm hoping my next student, who will hopefully graduate in about 2 years, get to do that with him. I really do hope so.
Yeah. I mean, they're going to change it up too. It used to be part of the main ceremony, but now they're going to do it per college, I guess.
Oh, okay.
Maybe.
So less people, I guess. Yeah.
Well, thankfully, the times I did it, the hooding ceremony was first, and then they read the 1,000 or whatever undergrad names. It's actually more than 1,000, I'm sure.
I'm sure it is.
Should we look up the speedrun record on Mike Tyson's Punch-Out?
Yeah.
Do you want to know? Actually, I think they do it based on total clock time in game, so I don't know how meaningful it is. But people have beat this game blindfold, which is absolutely
How can you do that?
So they listen
Just
to
that-
audio cues, and there's something called it's buffering, where basically if you hold an A button now, it'll freeze your punch until a certain time, and then it'll release it. And so they like control when the punches happen, and they do the cues based on the sounds they hear. Which is, again, they've figured out all the nuance that happens. And the math family tree. Reese's Pieces, thank you very much for sharing that. I'm going to dig through that and just go back and see how far it goes. All right, we're at 9:30. If anyone has questions, Ask a Scientist Gaming, mediocre gameplay, expert science. Today we have condensed matter physicist Christianne Beekman. She's happy to answer questions, particularly about magnets. Mostly your expertise is in that domain. Turns out that applies to a lot of things from quantum computing to, I don't know, measurements. A fun factoid I learned from Ryan Baumbach, I don't know if you remember the news story about the frog floating in a magnetic field, but apparently that was the mag lab. They got in trouble because it was an experiment on a living creature.
They're not allowed to do that anymore.
So that's part of your orientation now, don't float frogs.
Pretty much. Yeah.
Do you know which instrument they did that in?
Probably the 45 Tesla.
45, that's enough to float a frog. Frog becomes magnetic, induced field. I'm genuinely curious where they got the frog from.
Probably the pond in the back of the
Just somebody
lab.
went out there and
And we have a nice pond back there, so
yeah.
pretty sure. I think it was Jim Brooks, the late Jim Brooks, who actually.
He's the one that did it.
I think so. Yeah.
That's pretty amazing. I mean, it got a lot of publicity. Good or bad,
Yeah.
it was an interesting experiment. Theoretically, you could float a human. The question is, how much field would it take? So this is the second time you're fighting Piston Honda, is that right?
Yes, correct. But I'm pink the whole time.
It gets progressively harder. Let me know if you want the cheat codes, because we can have health, infinite health, we can have stars, whatever you want. We can make your life easier if you don't want to grind.
The grind is part of the fun, I think.
Yeah. Is Pluto a planet? Strong opinions?
Is Pluto a planet? Well, the astrophysicists say it's not. Not anymore.
Yeah.
It used to be, but then it wasn't, and it's still not, as far as I know. I don't think anybody has changed their opinion on that.
I mean, I really respect the decision to not make Pluto a planet. Not anything personal against Pluto, but is a really underappreciated thing in the sciences is when somebody comes along and says, here's the standardization of something, right? Like, here's the true definition of monopole, or here's what one sun actually is across the globe. Like, that standardization is necessary for any classification system, any descriptive science. You need to have that classification.
Yep.
And so they said, well, if Pluto's a planet, then these dozens of other things also would have to be a planet under that criteria. And they said, nope, we got to draw the line somewhere, and Pluto is on the opposite side of that line. So, yeah, Cuddle Puppy, we'll fight at a Burger King parking lot, 4th Street in 10 minutes. Is there a Burger King in Tallahassee? I don't even know. There has to be
A
somewhere.
Burger King?
Yeah.
Yeah, many. I mean, right? I mean, I never eat there, but
I know there's a McDonald's up Tennessee, but a Burger King.
there's one on Park, and on the corner with Park and Magnolia with the Winn-Dixie there. I drive by there all the time, and it was closed for a long while. I don't know why. They were doing something to the roof.
Oh, there's one just north of campus next to the Jimmy John's. That completely escaped my memory. Yeah, on Tennessee Street. Reese's Pieces knows. So, Cuddle Puppy, I'll see you there in 10 minutes. Just kidding, I'll be on the stream. How about 11:15 after the stream is over? We'll fight about Pluto being a planet.
I guess I had to start over again.
Man, that's fun, though. Going back to the start of our detour, like, graduating your first student is it is a milestone.
Yep.
Like, especially the first time
Absolutely.
you're, like, at that authority position and you
Yep.
have to mentor someone. It's...
And it's, after 4 years of hard work, maybe 5, right?
Mm-hmm.
So, but yeah, then I suddenly graduated, 2 students in 2020. So yeah, that was at the height of the pandemic. Everything, including the defenses, they were all on Zoom, and it just wasn't the same experience as obviously I had hoped for. But, yeah,
Well, I mean,
it was still a milestone.
the pomp and circumstance of defenses in the U.S. is... I don't know what it was in the Netherlands, but, like, did you have, like, an official ceremony with an opponent, and like, what was your defense like?
So the ceremony is much more official, I would say, in the Netherlands. So you are with your family, you're doing the actual defense. So you're being grilled by your PhD committee with your family sitting behind you. You're all dressed up, and dress codes and everything. Men have to go in, how do you call these things? Tall hats and like the penguin suit. There's an official word for the suit, but I can't come up with it. You have 2 people with you for support. And then your 5, 6 committee members that are grilling you. Or your family is sitting there. It's a very old building, very historical. And then, they go away and deliberate, and like always, and you're waiting, and then they come back with, hopefully with the degree in their hand.
Is the likelihood of failure, I mean, is it similar to here, or is it...
Oh, once you're there, you're probably not going to fail.
so
I mean,
so-
unless you refuse to answer any questions. I don't know if that ever happened, but
I see. So it is a whole lot of pomp and circumstance.
yeah. But the point, your thesis is completely written, completely finished. There's no changes after that. So everyone has approved it, but you still need to show up and do a decent job at answering the questions.
Yeah. That's fun.
So it was fun, and was a whole long evening of food and partying after that. Yes. So maybe that was a different kind of milestone, I guess, but very important. But I guess the one that was really where I felt, yeah, now I'm actually like a professor and I'm doing what I wanted to do, was when I graduated my first student, right? That's a whole different, level of that same type of.
You hope they get a job and go on and do bigger and better things.
Yeah, all three of my students got very good jobs, so very happy with that too. That's also very important. You don't want them to, well, it depends on what they want. I mean, not every PhD student wants to stay in academia or even go in industry, but it's very important they get jobs that they're happy with. So.
All right, back to a science question, kind of a science question. Critical Ninja wants to know, what would be the benefits of floating a frog or any living creature?
Isn't everything allowed in terms of science? No. Can you? Isn't that valid science question? It's a very pointed hypothesis.
Yeah.
It cannot float a frog in a magnetic field.
The answer we know now is yes, but until somebody does it, it's still a testable hypothesis.
And unfortunately, if you wanted to, keep somebody, let somebody experience weightlessness, right? It might be useful for somebody who struggles with, walking and whatnot, right? You can relieve that, but it's obviously not allowed to put people in a high enough magnetic field that you can float them. So, yeah. But there could be benefits to being able to essentially float people, make someone weightless, right?
Yeah. Yeah, I'd be curious about the implications of that, because I mean, you're inducing fields within the body, you're aligning moments.
Right.
Like, are there negative repercussions? The answer is probably yes.
Yes, but we wouldn't know exactly what.
Yeah, and I guess it would depend on how long that is. I mean, definitely doing that. They found a lot of animals that go north-south. They have guidance systems based on magnetic fields. I mean, I can't imagine a huge field not damaging the systems.
Right. You have to, any form of radiation, right? It's gonna, if it's altering something in your atomic, not the structure perhaps, but it will alter electronic configurations in your body. It will create excited states in atoms potentially, and align all the magnetic dipoles that you have. I mean, I don't know what that would do.
Yeah, I mean, at some point it has to affect the motion of hemoglobin in your bloodstream.
Yeah,
right? There's directionality to the field probably matters.
Yeah, probably.
So, I mean, people were not wrong to be upset that we threw a frog in a magnetic field, because it probably did something to the frog, but.
And what about our signals in our brains? They're electromagnetic in origin. Those could easily be disrupted, and who knows what that will do. You're unable to process something, that would be not great.
Yeah, and I one of the things to note is the problem wasn't necessarily suspending a frog in a magnetic field. You could write a justifiable proposal to want to do that. The problem is they didn't get the proper approval. There's something called IRB approval, which is Internal Review Board, which basically anyone that studies any living creature, whether it be a worm, whether it be a human being, they have to submit an application to get approval to do so. And so I do test analysis for my Gen Chem class, looking at statistics on exams, and I don't use any personal data from the students, but the fact that I'm using their test data, I have to get IRB approval just to do that analysis and publish it. And so floating a frog, obviously, or affecting a living creature, you have to go through the right channels.
Yeah.
And it probably wouldn't have been approved unless there was a justifiable reason to do that experiment. But especially vertebrate animals, that's a whole nother class. You can do it on worms and things like that. That's less frowned upon. But as soon as they have, vertebrae or a spinal cord and nervous system, then it gets much more challenging to do experiments on living things. So we're glad those systems exist, but Apparently Brooks did not care in that case. He just went.
Well, he was a authority on himself for doing this kind of stuff.
He was very old school.
Yes, yes.
It was just like, that's an interesting idea. Let's give it a try.
He was always in for some fun and trying new things.
Yeah.
No, you know, you don't ask for permission. You ask for forgiveness later. Usually the best way to go.
Yeah.
But they did float strawberries at some point too.
Oh,
really?
Really?
Of course,
That was
you know.
less sexy, apparently.
Yeah, but you know, it's safer, I guess, or less frowned upon in any case.
Strawberries and frogs.
Yeah, yeah.
I didn't know about the strawberries. That's really fun.
Apparently, there's you know, in any material, if you have given enough magnetic field and you align the dipoles, you can make it work. But
I mean, that's intense to me. I mean, you're inducing a magnetic moment in a non-magnetic thing.
Yes.
As long as the field's strong enough, that does occur. Mm-hmm. And actually, most of you are really happy that happens. That's how MRIs essentially work, and why we can view inside the body without cutting people open. MRIs are just big fields, and looking at relaxation times in those fields, it's constructing an image. So, yeah, whether you need to float someone or not is another question. Don Flamenco, that's what his name is. I completely forgot.
This one is among the easier ones to do.
It's pretty boring, but
because you can induce the punch, like punch him, he will, and punch back, and then it's
And there's all sorts of little tricks in this game, like if you alternate punches on certain ones, it'll indefinitely hit them, and it's left hand only, it does something. I don't know. People have figured out, I pay a lot of attention to retro gaming and people speedrunning, and the tricks they found out are absolutely
if you do this all the time, I'm sure you come up with things.
Oh yeah, you reverse engineer the software and figure out every nuance of the game. All right, we should probably do another one of our predictions. Which one do you want to do?
Let's see. Why not about the super?
Which one?
The room temperature.
Yeah, that's a fun
that one.
Listen, I look forward to seeing what the answer is on this one. All right, if you're not following, click follow, get your standard internet units. It's time to gamble on another prediction question. Another science question related to room temperature superconductivity. Don't Google the answer. We're going to have you answer the question as you know it now while watching Mike Tyson's Punch-Out, King Hippo, Fight for the Ages. All right, we're going to throw up the prediction right now. The question is, room temperature superconductivity has been observed. Is that true or false? As somebody at room temperature, which I think is defined as anything above, like 10C or something
like that.
Has room temperature superconductivity been observed? True or false? Put your predictions in there now. Gamble your points is depending on your level of confidence. For those of you that haven't done predictions before, click the predict button right at the top of the chat, and then you can bet however many points you want. You can do 10 or a custom amount. It's totally up to you. The question is, room temperature superconductivity has been observed. Is that a true or a false statement? This is a fun one.
I like it a lot too.
Yeah, I'd like to see where these go. And this is, so I do a lot of test analysis for Gen Chem, so I spend a lot of time thinking about test questions and stuff and distractors. I just never know how Twitch is going to answer these questions. I mean, some of them you think are easy, but then there's like meta information, like why would they ask if the answer wasn't this? So it's always a fun exercise in writing these. And Christianne was kind enough to go back and forth with me on a few of these questions so we can clarify and simplify, and we're back to the magic app. All right, you guys have about 30 seconds left. Room temperature superconductivity has been observed. True or false? This is the idea of conducting electricity with essentially zero resistance. Have we achieved that at room temperature? Is the answer true or false? Pick your decision now. 5 seconds left. Guess or, know the answer. It's totally up to you. Yeah. This one's contentious. It's actually the same number of people voted, but the person that said false was very, very confident. And so the answer actually ends up being true. Room temperature superconductivity has been observed. There's a qualifying statement here, though. Do you want to reveal that?
Right. So it, well, it wasn't room temperature, meaning like 15 degrees Celsius or so. You did need a very, very, very high pressure applied to the material.
So I looked up these numbers. It's 267 gigapascals, which is the equivalent of 10,000 atmospheres of pressure.
Yeah.
And so to give context, that's 147,000 pounds per square inch, which is like putting a tank on a 1-inch like pedestal, which is kind of crazy.
Yeah.
And so congratulations to Critical Ninja, who said true and got a 21-to-1 payout on this one.
Wow,
So
congratulations.
Yeah, this one, if you press something hard enough, you get weird behaviors, is the answer. So you do a lot of low temperature plus high field. You do high pressure measurements as well?
No, I mean, not really, because that really takes a whole nother set of very specialized equipment. And so it's possible to do it at the Mag Lab. And so I do have collaborators that focus on that. And so we have in the past collaborated with them if we wanted to try high pressure stuff. But it's a whole nother challenge. Because now you're adding another degree of freedom that you need to control, right? You already have a very high field, a very low temperature. You then put more in your cryostat, in your field, which also gives you more magnetic background. So that's always a challenge, is, how do you deal with the extra material you have in your magnet and giving off an extra signal that you have to separate out from your measured signal. Background subtractions are real. Well, every field has to deal with that, but background subtraction is a real problem.
Well, especially when your signal is very small and
If you're doing thin film materials, when you don't have a lot of material anyway, you already have a big background from whatever substrate you're growing your sample on. Yeah.
So there's the Nature article in chat if you guys want to take a look. They took carbonaceous sulfur hydride at 267 gigapascals, and it became superconductive at 15 C. And so if you press stuff hard enough, it acts weird. Is what we learned from that study. And there's a bunch of examples of that, right? Maybe not 15 C, but if you press pretty much anything hard enough, it'll do some weird property. In this case, it's superconductivity. What's interesting about this paper, and when I was looking this up, is they did a bunch of editors' notes on this, where the editors said, well, Nature has been alerted to undeclared access restricting relating data behind this paper. Then the data was posted on archives. Then Nature's been alerted to some of the data may not have been processed and interpreted correctly. So is this accepted as true in the community now? Or is it still...
Sure. I mean, I think it's true. But again, you have to take it that it's true, but under very specific and extreme circumstances, right? You have to really apply extreme perturbations to the sample in order to make it happen. So, does superconductivity exist at room temperature in what we call ambient, right? At your average pressure, 1 atmosphere, then the answer would be no. Right? So, can we use superconductivity now in like the electrical grid and really cut losses there? No. I mean, we're not by any means there. We don't have a true room temperature in ambient functioning superconductor.
So do you know off the top of your head, 1 atmosphere pressure, what the record is for superconductivity?
So there's a recent story, fairly recent, which is actually in iron selenite monolayers, or really thin films. And when you grow those or make those on strontium titanate, there's something with the interaction with the substrate that leads to a relatively high superconducting transition temperature. So for bulk iron selenite, it's something like, of the order of 10 to 20 Kelvin, right? It's not high, it's fairly low. And then it becomes something like around 100 or slightly over 100 Kelvin. That's a major increase in TC, the critical temperature.
So it's minus 170 Celsius roughly.
Yeah, but at least with liquid nitrogen, you can get there.
Yeah.
So that's already a lot higher temperature. I mean, that beats a lot of the COOP rates, the true high temperature superconductors that we know about. And we don't actually really know what the mechanism is behind that large increase of TC. But there's something to do. I had some chats with a theorist who unfortunately passed away since at the Mag Lab, Gorkov. Some people might know him from the Gorkov equations. But he, I believe, was of the opinion that it had something to do with phonons, which is again is moving atoms. So we come back full circle to our moving atoms, right? And temperature, and so yeah.
Turns out moving atoms are both great and a terrible problem.
Yes, they are.
It's a thermodynamic limitation in solar cells and light emitting diodes and magnets, and pretty much everything is limited by atomic motion.
Yep.
I mean, so one of the other questions we like to ask, and maybe it's a follow-up on this, is what's the next major breakthrough in your field? Is it a superconductor at room temperature, or?
Well, the field is large, so superconductivity, I would say, could be a separate field from the magnetism field that I would say I'm in. So yeah, room temperature superconductivity is one. It's difficult to predict if that's ever going to happen. In my field, I would say a quantum spin liquid is probably the biggest thing. And also, some people claim that it's already been seen or in some materials, but there's also a whole nother camp of people that are like, okay, so now you have a quantum spin liquid, which is like a very frustrated magnetic system. So it will not order even to like pretty much absolute zero. Lots of entropy left. You measure it sort of through spectroscopy techniques or entropy techniques. But the problem with these techniques is often any disorder in the system could lead to signals that mimic a quantum spin liquid. So how do you know you've got the real deal on your hands? And I don't think we can make samples clean enough.
So I guess that's so what's the explain it like I'm 5 for the quantum spin liquids? Because they're not actually liquids, right? They're liquid in behavior.
They're not liquids, they're solid materials, but they're magnetically, so really electronically, they behave completely as a liquid, if that makes sense. So the electronic degree of freedom is randomized, right? So high entropy state.
So their atoms are mostly fixed like a solid, but the electronic properties are much more mobile within that solid.
Exactly.
Those moments around, and dipoles are mobile, and very, again, weird properties.
Weird properties, and then you start to see that in those systems, you can get what you would call fractionalization of your electronic degrees of freedom. So now you can actually split the orbital, spin, and charge degree of, they now become sort of separate properties, and have excitations like called spin-ons, and so you can sort of separate those degrees of freedom. So it's pretty. Those are pretty exotic excitations that you can have. But then the question is again, can you? So when do you know you have it on your hands? The real deal, right? I mean, the smoking gun. That's the question, because with so much disorder in the sample, you'll get diffuse scattering and all kinds of spectroscopy techniques if you have disorder in your sample, just in the atomic lattice already, right? So you have to make your sample pretty perfectly clean. How do you prove that you have that?
But you think if that comes through, that will be a Nobel Prize? Somebody definitively shows that as being real?
Possibly, yeah.
Yeah.
I wouldn't rule that out. Yeah.
No, that's fun. I mean, so it might have been observed, but the person that says, here is the definitive evidence, that's going to be the game changer. And it may or may not happen.
Right. I mean, people are looking.
Yeah.
And some people claim to have seen it, and sure, they see evidence for it, sure, but how do you prove? Right now, you're trying to show that you have a complete absence of order, right, in your system. So it's almost like a null result in your measurement, right?
Yeah.
Because static order is easy to measure in a system, right, of whatever kind. If you have ordered electrons in any way, charge order, or they're magnetically ordered, right, that's easy to measure. But when they don't do anything and all you've got is a low temperature state with plenty of entropy, that's not so easy to measure.
I mean, so physics is unique in its position, and often you'll have people that show like things that cannot happen, right? And is this one of those things where people are arguing it's an impossibility? Oh, nice.
Sorry, say that one more time.
Yeah, no, you're focused on the both large, I understand. so physics is in a position that there's a lot of people that will make arguments about physical impossibility, like faster than speed of light, going back in time. I mean, are there people writing papers saying these quantum spin liquids are physically impossible, or is it just we'll never be able to know if it is?
No, they're not impossible. I mean, theoretically, they certainly exist, and there are good claims that in what kind of systems you should be looking for them. My big concern is how do you know that you've made your sample clean enough that you can rule out other sources of entropy and disorder in the system that will give you sort of a false positive in your measurement, and so that you have multiple different people.
All right. If you don't object, I'm going to give you superpowers.
Please.
Are you ready?
Yes.
You want it? So we're going to turn on basically everything. So you are going to absolutely wreck these guys until you get to Tyson. Then it's going to be
okay.
Right.
So
5 knockdowns in the first round. Definitely fight of the year. That is a pay-per-view special. You guys get it here for free. Sorry.
Let's see what happens. I don't know what I'm...
So we put in cheat codes. Basically, it's you keep your hearts, you keep your stars. Your health doesn't go down when you're punched. His punch is damaged less, you're damaged more.
Essentially, I don't have to pay attention anymore.
No, you don't have to at all. You've been noble all night in not using cheat codes, but there's a certain degree of freedom involved in, you are unlimited health and your punches do.
I don't remember if I ever got past that second round of what's his name, Honda.
Piston Honda, yeah.
I don't remember honestly how far.
Well,
I didn't play this that often.
It's a war of attrition. So I'd never beat Mike Tyson without Game Genie codes.
Okay,
so
well,
I use the cheat codes to get that far and beat that. But and people can do it blindfolded. How hard can it be?
Well, then you're spending too much time we don't have.
Yeah. I mean, I speed run games, so I won't make any claims about other people.
Sure, if the
yeah.
But if it's hard to get to that stage, I think.
No, it absolutely is. You have to practice a lot.
There's a lot of time that goes into that.
Well, in their defense, there are people that get paid, $250,000 a year to play video games on camera, which is incredible. So they just full-time dedicate, isn't it?
It's an intriguing industry where, yes, people will pay to watch other people play games.
Yes.
I don't know if I quite understand it, though.
Yeah, I mean, the Twitch is a weird thing because it's this social interaction. Like it's like a podcast or TV show, but there's an interactive element. And really, I think people are paying for the engagement and the interaction and the responding directly to chat questions and things. Which is why I love it too. It's real time, like comments and questions, and really perfect for science Q&A. Plus some video gaming in the background, which is kind of fun.
Oh yeah, I'm enjoying this. It's been so long. Now I need to maybe invest in a NES emulator or something like that.
What you should do is get a Nintendo Switch. I don't know if you're familiar with the new system, but you can get all the retro games, but it also has new ones like Mario Maker, where people can make Mario levels. So there's literally an infinite number of Mario levels that you can play. And it's like really hard to really easy. You pick the difficulty levels. It's pretty incredible.
Yeah, I think I've seen that. I don't know where, but the Switch
Yeah, it's worth it. I have one.
Okay.
So aside from the old NES games, I play Mario Maker, which is fun. I mean, people are creative. They make an infinite amount of garbage as well as some good level in there. So you get a mix of a little bit of everything. Yeah, speaking of which, we've crossed the 10 o'clock mark. Anyone just joining us, Ask a Scientist Gaming, mediocre gameplay, expert science. We're playing a little bit of Punch-Out while discussing magnetic materials, magnetic quantum, what was it, quantum liquid?
Quantum spin liquid.
Quantum spin liquids. Pluto being a planet, what else do we...
I work on spin ISIS, by the way. That's the frustrated magnet that is not a liquid, because again, how do you prove that you've got a quantum spin liquid on your hands, which if it's already hard in bulk samples, it's going to be impossible in thin film samples. So yeah, my focus is more on spin ISIS, which have the monopoles.
Just fun. Temporary monopoles.
Yeah.
So no one gets up in arms. Not permanent claims.
The topological excitations equivalent to magnetic monopoles. How about that?
I guess that's the question. So what are you most excited about over the next 5 years of research? Where are you headed? I guess you don't have to reveal too much on stream, just in case somebody's going to scoop you up based on a YouTube video. But where do you want to go with your research?
Well, I think getting a better understanding of these, what we call quantum magnets, that's a much larger scope of materials, will be great. Just for me, for mostly fundamental questions, right? I like to manipulate materials and answer fundamental physics questions, but there's also clear implications for quantum computing in there if we can make it work, at a higher temperature. That's a big if, but it would be great, of course, if one can dream about something that may or may not be possible, then that would be it. But from a material science point of view, I would say, getting to a stage where we can comfortably design materials according to whatever outcome we want. So sort of a materials by design research approach would be great. But that requires, a big effort from, experimentalists and theorists together, because we need more predictive power for that, right? I can try to manipulate my atomic distances all I want, but, phase space is huge. So I think we do need to be better informed by theoretical work in order for that to really happen. But like you make stuff on order. Okay, we need something that's magnetic in this way, or magneto-optical properties or whatever. And we need these atoms, they need to be this far apart, and we can make that. Then you're really a sort of a materials by design.
I mean, so one thing we talked about Steve Blenner with is he wants to do a high throughput where he matches lipids and gets properties of those lipids. I mean, can you do a high throughput version of what you do? Or is it just too hard to measure on a multiple sample scale?
Measurement take time for sure. Sample fabrication also takes time. So we do pulsed laser deposition, which means I need a expensive laser. Assuming everything works, right? Everything is operational lab, which we all know as experimentalists, stuff breaks all the time. But let's say
months.
Yes.
Literally months of time.
Yes. So yeah, if everything works, sort of lost my train of thought there.
No worries. High throughput.
High throughput. Thank you. So we can grow probably at best 2 samples a day.
It's just inherently slow.
Yeah, we need good vacuum. So the pump down takes a couple hours. Setting up takes an hour or so. Heating the heater, right? We do everything in sort of a solid state reaction. Not quite solid state, but we're talking temperatures of like 800 degrees or something like that. It takes time to do all of that.
And so with all that effort, how many of your samples are just garbage out the gate?
Depends where we are in the process, right? If initial samples can fail horribly, but then we'll do some X-ray diffraction, figure out what we've made. Is it what we wanted? And then we systematically tweak the growth parameters till we get it right. So that can be, weeks to months of, trial and error to get it right. Once we have it right, then we can start doing the interesting stuff and start measuring the magnetic properties and go to other labs and do neutron diffraction, synchrotrons, all that stuff. We use that too, but only once we've done all the trial and error, all that legwork of getting the it's a new guy here.
Yeah, Popinski. He's pink for some reason.
Yes, very pink. So yeah, measurement is then the next bottleneck, right? Okay, we can make 2 a day, even if we did produce 10 samples a week, so roughly or something.
Yeah.
We still rely on the availability of measurement time, and so we don't get measurement time every week in the big magnets. So, you have to wait in line, you have to write proposals. And so, we go get a couple weeks at Oak Ridge for something. We get a couple weeks a year at Argonne for something. We get maybe 4 or 5 weeks at the Magnet Lab per year for stuff. And, it's enough to get your publications. But, and the rest of the time we're trying to get ready for those weeks that's happening, right? Because then we have to be on the money, because you pay for travel, you invest all the time, it better work.
Yeah.
And it doesn't always, right? I mean, also stuff breaks at national labs.
Yeah. No, that's tough. Speaking of equipment, what lasers do you use in your pulse laser system?
So we have a UV laser, so wavelength is 248 nanometers. So it's basically concentrated, coherent sunshine. Sort of.
248 nanometers. What kind of laser is that?
It's UV.
Yeah. Well, it's UV, but I guess, what is that? An argon laser? It has a gas mix of neon, helium, and fluorine gas. Okay. And that gives you...
And krypton, a few other things.
That is a high energy photon.
Yes, that is definitely. So it's a class 4 laser.
Yeah.
It's not, it's, as I said, if you stick your hand in that, you will not actually have a burn right away.
Yeah.
You will get a sunburn later.
Well, you get a sunburn on both sides of your hand because it'll go all the way through.
It is pretty high energetic, and maybe some increased risk of skin cancer. But,
Such is the risk of research.
But
the worst part is you can't see that laser, so you don't even know if it's on.
Actually, it's so we have some attenuators in it, and so you do see sort of a bluish light.
I see. So you see the second harmonica. Then
you see something. It's not super bright, of course, but you see something. And it's enclosed most of the time, unless I need to do alignments. Yeah, which is not terrible. I mean, it's pretty easy. It works pretty well. Yeah. It's high power, sure.
So you just use like a business card that fluoresces under UV?
Actually, we used thermal paper, like fax paper. Okay.
Yeah. Fax paper. That's fun.
It's hard to get, so that's going to be a problem in the future. And you can buy like new stuff. It's called Zap It, and it just isn't good, right? Because somehow it doesn't show me the spot in the same way as just like thermal paper does.
Wow.
So I still go back to my thermal paper, and then I get to see, and my student uses thermal paper, at where it hits the target material that we're trying to evaporate to see, how large the spot is, and we calculate fluence that way, so we know exactly how much energy we're pumping per square centimeter in our target that we're trying to evaporate.
Fax paper is a really fun idea.
Yeah.
You can go to like Thor Labs or Edmund, or they'll sell you like laser optic paper.
Yeah.
But
but it's not as good.
And it's expensive, and
it's not as good.
And it doesn't work as well.
It's definitely not as good. So I would say go with thermal paper if you can, and it works great for my my UV laser.
Yeah. Well, thankfully for us, most of what we do is visible light, so you actually get to see the spot.
Mm-hmm.
You can see it on business cards and a line from there, but yeah. Second round of ball bull. It's fun.
How far away is Mike Tyson?
3 or 4 more fights away. So not too bad.
I'm not doing a great job.
It's a hard fight. It's fine. We got cheat codes in. One thing to note about Bold Bull here, the only way you can knock him down is either on the charge or when you use a star on when his health is down really low. So I don't know if you've used a star yet, but you have to press start and it does a super punch. So like if you pause him there and then stun him once and then use the start like that. Yep. There
Okay. That's I never knew about that. Interesting.
Yeah. So those stars up in the corner are a super punch.
I see. Well, that's good to know.
Yeah.
Learning new things every day.
No, that's why we do this. We learn about games. We learn about science, which is exciting.
Yeah. No, my laser is fantastic, by the way, but yeah, it's not trivial to keep it running.
So the PLD system, that's your system? That's your personal
completely dedicated system.
Yeah, so that's high, super ultra high vacuum, turbo pumps.
Yep, turbo pumps, yep.
Oof. Even that is, I need to keep it clean, vapor deposition any kind. How often do you guys clean your chamber?
Not very often, but the key is not to use anything too crazy in there. So I do limit what we will grow or what we will try. Nothing too crazy that will potentially cross-contaminate.
Yeah. Makes sense.
Potential future growth. So yeah, so no bismuth or something like that will, or lead that will go everywhere. Right?
Yeah, it's permanently in every sample.
Yes.
From then on.
Yes, that cannot happen.
Yeah, when I was in grad school, we did the vapor deposition, but if it was like OLEDs, so thin film growth of organic things, and there's always like you put a porphyrin in there and it's everywhere indefinitely, and you have to do full chamber cleaning, and your stuff is way more sensitive than anything we do, especially thin film. It's like any impurity changes everything.
It can definitely change properties.
Oh, so close.
I know, I was just about to hit the start button.
Rank
I thought I had it.
There might be only 2 fights left after this one. 2 fights and then Tyson. Because there's Sandman, there's the Hurricane guy, and then I think Tyson will be your third one. You might as well commit. I mean, typically we start an arc at about 10:30, so you still have 15 minutes.
I'll try.
Yep. So, I mean, mildly related to what you do. When I get on an airplane and somebody asks what I am, I say I'm a chemist, and they're like, I hated that class. And then I have to explain I work on solar cells. What is your airplane conversation? Like, do you tell them what you do, or?
Sure, I'll tell them. Well,
when you say physics, they'll be like astronomy or particle physics, right? They don't necessarily think condensed matter.
Right. So I'll tell them condensed matter. Well, actually, no. Sometimes I get that far in the conversation. Other times they'll just say something like, "Oh, smart girl," in the conversation.
The end of it.
Honestly, that happens a lot too.
Oh, yeah, you must be very smart.
Which I sort of hate because I then actually don't get to tell what I do, which is sort of annoying.
Yeah. My favorite interaction when I told somebody I was a chemist, it was like in Atlanta. It was the Atlanta airport. It was outside of the bathroom. And like this guy asked, "Oh, what do you do?" I'm like, "I'm a chemist." And he's like, "That's badass." Fist bump, and then he walked away. I'm like, yes. Oh no. Press start. It'll go back to, I think it'll fight him again. Oh, is it over?
Yeah.
We had 3 continues. Oh, we added our thing too late. Yeah, go ahead and press continue. Let's see
We'll see what happens.
I think it'll bring you to that bald bull fight.
Piston Honda again. I'll try to be faster this time.
I'm going to see if we can get the codes. We're going to have you fight Tyson no matter what. Oh no, this is the furthest you can go. Let me see. So we can go from this one, we can skip to Super Macho Man, which is the one right after Bald Bull, I think.
Okay.
You want to do that?
Yeah, let's do it.
So, restart you. Let's go to that one. Press start, I think, where you can start pushing in numbers. Select, maybe? No.
Nope.
Let's try select. Press up and down. Yeah, there we go. 2.
Oh.
I think it's going to be left and right.
Okay.
2, and then probably A. 3. 1. 7. 5. 0. 7. 4. 3. 8. Huggy Bear knows the Tyson
Oh,
code.
no.
Oh, no.
Guess I pressed the wrong one.
Oh, let's try it again. All right. 2.
2.
3.
3.
1.
1.
7.
7. Was there a 5?
0. 7.
7. So what do I press after?
7. 4.
Because start ain't it.
8. Maybe press A again. Is that what you've been pressing?
Yeah, and that didn't work.
So it might be start. I apologize. We're figuring this out as we go. All right. 2, 3, 1.
2. I don't think it was start either. That's what I tried first.
Oh, Huggy Bear, what button do we push after we put the code in?
5.
750.
7. 5. 0.
7438. You need an answer from Huggy Bear after.
3. 8. I think I tried A and start already.
I think those are the only options. I don't know how it would go any other way. That's awesome. Memorizing the code since your childhood is pretty amazing, Huggy Bear. Thank you for doing that. I don't recall which button to push. Well, it's not much. All right, let's jump to Tyson. Time is running short. Be ready for... Let's see if we can do the code.
Yeah.
Tyson 007 3 7 3 5963. This fails. I don't know what it's going to take.
What did you push? B?
I pushed the start button.
Oh, maybe I didn't. Oh, yeah, there he is.
There we go, ladies and gentlemen. Mike Tyson. All right, while you're fighting Mike Tyson, Huggy Bear has a question. Good evening. I'm fascinated by magnet. Is that in your wheelhouse? Not sure if magnetoelectronics is related. Yes, magnets are most definitely in our wheelhouse. If you guys have questions about magnets or Mike Tyson Punch Out, she's happy to answer those questions. He is hard.
Okay. Any advice here?
So in the absence of Game Genie codes, any of those punches would knock you down immediately. So let's kind of get out of the way and punch him as much as you can. And thankfully his health doesn't refresh, because every time he hits you without the codes, his health fully returns. All right. Miranda wants to know, hello, this is a very cool stream. The last time I did any material science was undergraduate research ages ago with graphene. Does that have any applications or relations to your research?
Well, graphene is a very interesting material. It's a monolayer of carbon. And, well, actually, it's interesting because it has... It has very different properties in the monolayer form compared to, let's say, what you have in your pencil, right? Graphite, right? Which is essentially the same material, but now you exfoliate it to a single monolayer, and suddenly now you get all these enhanced properties like super enhanced material strength is one of them, right? It's much stronger than you might think, a monolayer of atoms like that. If you have it on a substrate, you get interesting rippling effects, which changes a little bit the atomic arrangements, which can change the properties as well. So it can also be quite conductive, even though you're only conducting electrons across a single layer. single monolayer of atoms, right? So that's pretty crazy. So yeah, it has a lot of interesting properties that you would not find in the bulk material graphite. I'm afraid I'm doing very little with this Mike Tyson.
No worries.
I punched him a few times.
Cuddle puppy. It's not at all strange for the for boxing to let a 0-2 flyweight fight versus a 31-0 heavyweight champion. You're right, Cuddle Puppy. This game is so unrealistic.
Definitely.
Sorry, I missed the answer on the graphene. Was the answer is it's interesting and scientifically intriguing, but not applicable yet?
Oh well, I was saying it actually. Graphene has it's quite a strong material. Amazing, and it has also, it can be quite highly conductive as well. But of course, as always, you're also prone to disorder even in a monolayer of carbon atoms, and so you have the you can have ripples, for example. I'm trying to punch him now.
His health was coming back. Yeah, Tyson is tough in this game.
So we talked about that, and let's see what else
Is graphene used in a commercial product?
Not yet, but I think it could be. I mean, it has plenty of interesting properties.
I mean, I guess processing and handling.
Will he ever stop punching?
He will not, unless you block enough in a row. Down to a decision.
Oh, he's already won. Because I didn't do enough damage, I guess.
Huggy Bear follow-up. Have you heard or worked on trying to find anything similar to magnetism in non-ferrous or non-metallic materials?
I work on non-metallic materials. That's a great question. So most of my materials are actually insulators. And the one that we've recently published on, both ones that we've recently published on are actually magnetic, or are magnetic materials, but also really good insulators. So yeah, I would say I generally don't work on metals, and generally my systems also don't have iron in it. So they're both non-ferrous and non-metallic. Although the material I work on does have the interesting property that, so to give you a chemical formula, maybe cobalt V2O4 spinel material. So I do like my transition metals. Iron is one too, by the way. Vanadium, sorry.
Oh,
cobalt
vanadium.
V2O4.
V2O4.
Yeah. A different spinel. And so it's interesting because it does a few things. It's an insulator, but you can theoretically make it metallic if you can squeeze those vanadiums closer together. And so in the class of compounds of spinels, this one is the closest to that critical vanadium distance. So I'm interested in this one because it's also frustrated, and it could potentially become what we call itinerant. And those are two interesting things coming together that could potentially help us with that quantum spin liquid problem. So
Tyson is so fast. If anyone hasn't tried, you should download the emulator for this game, put in the Tyson code and their cheat codes, and try to take on Tyson.
It's impossible,
even
people.
With all the codes, this is very, very difficult.
And somebody beat this here?
Oh yeah, no, people have beat this blindfolded, which is absolutely amazing.
I don't even have a star for any
Yeah, super punches. No.
But I hit him 2 times already.
Yeah, every one of these punches knocks you down if you don't have cheat codes. So.
But yeah, so my work is mostly in oxides. So transition metals, rare earths as well, with some oxygen surrounding them, and we control the magnetic moments by choosing which atoms we put in them, like the cobalt and the vanadium both have magnetic moments, but also by their oxygen environment. Or what we call the crystal field, but chemists call the ligand field. That's another one of those examples of different language that determines everything about how magnetic the system is going to be, where this magnetic moment's going to point in within your crystal, and so we try to manipulate that.
Comfy 420. Oh. Cuddle puppy. Close enough.
Yes, that's
oh wow, we got a knockdown.
No.
Ladies and gentlemen, we have one knockdown.
I have no clue how I did it, but I did it.
Hard punch. That was amazing. I was going to suggest we do a prediction about will she knock down Mike Tyson, but speaking of which, we should do one of these predictions. About the measure samples at minus 460 Fahrenheit. All right, we're going to throw up while Christianne battles Mike Tyson. We're going to do another prediction right now.
I was about to use my star. He's still smiling though, so that's not good.
I don't think he ever shows damage in this game.
Oh, okay.
All right, we're going to throw another prediction up there right now. The question is, Christianne and her group routinely measures samples at minus 460 degrees Fahrenheit. Is that true or a false statement? So short of you guys actually reading her papers, you might not know this answer, but it is answerable in a pretty straightforward way. So yeah, make your predictions now. You guys can even Google search on this. If you find her papers and find the experimental section fast enough to answer this correctly, I'll be very, very impressed. But either way, throw your guesses in there. Does she measure samples at minus 460 Fahrenheit? Is that true or is that false? So throw your predictions in there now, or guesses. If you're not following us, click the follow button. One, that helps with our visibility and the number of people that are following us, but also it gives you 300 standard internet units that you can spend on questions like this, and you can make us drink alcohol or request factoids. Man, I'm impressed you got him down. That was one really hard punch, right? He had still had a bunch of health left and just knocked him on his butt. So I don't know how much you work with time scales of events, but one of the things that I find really intriguing about these games is depending on how fast your computer monitor is, you have a certain amount of response time to its actions. So if you have a CRT TV, it has like millisecond response time. A standard LCD has something like tens of milliseconds. And then I bought a specialty LCD for this that has like 3 milliseconds.
I see.
It matters what screen you play on and how fast your controller is, all sorts of stuff.
Wow.
So what's your guess? Is it, does Christianne and her group routinely measure samples at minus 460 Fahrenheit? Is the answer true or false? Throw your prediction in there now. Cuddle puppy. Someone did a Google search. All right, Christianne, what's the answer? The answer in this case has to be false. Bit of a trick question, Cuddle Puppy. You guys did the same math. You did the conversion for minus 460 Fahrenheit. It turns out if you do that conversion, that's actually minus 0.1833 Kelvin. So it's actually a physically impossible measurement, which is good for you guys for catching that. That's why we opened this up to Google searching, but yeah. Cuddle Puppy, yeah. No, it was a trick question. We apologize. I'm sorry if you got betrayed by that. But no worries. It looks like the betting was pretty even on this one. So kudos to you, Huggy Bear. Enjoy your standard internet points and your 1.15 to pay one payout. Congratulations.
We do routinely measure at positive 0.1.
Yeah.
0.02 Kelvin, actually.
All right.
So that's 458-ish for 459 negative Fahrenheit. So
yeah,
pretty close.
So Christian, you originally sent me that question. I did exactly what you guys did, and I looked up 460, and I was like, it's below zero. So we debated how to write that question, actually. All right. Are you ready for this? We're going to close the night with NARC.
Yes.
Ladies and gentlemen, if you're not familiar with the stream, we end every single stream. Every guest has to play NARC, or wants to play NARC, we'll say. But NARC is I think this is a 1988 Nintendo game. This is the War on Drugs manifest as a Nintendo game. So, Christianne, whenever you're ready, it is time to win the war on drugs.
Yeah,
So,
I'm
at
gonna
the very
try.
least, we will feel victorious having won this war. And we'll start the timer as soon as you touch the ground. And we are live, ladies and gentlemen. But yeah, it's a trick question, but also, I mean, it's one of the few questions that with a Google search, you guys can actually answer with certainty. Because, I mean, I guess, Christianne, you can explain this better than I can, but below 0 Kelvin is physically impossible. It's based on the rules of the universe. You cannot go below, you can't even reach 0 Kelvin. Miranda, did Nancy Reagan design this game? Might as well have. This is, the license plate literally says, say no to drugs. So are you familiar with the DARE drug program in the United States? Have you heard of this?
No.
Every high school kid has a DARE t-shirt. It's basically DARE to say no to drugs, and it's some kind of acronym for something I don't remember, but essentially it's this failed drug prevention program where the prevalence of drug use actually goes up when people go through this DARE program.
Interesting.
And yet it's still prevalent in schools. It was Nancy Reagan and the Reagan administration decided to declare war on drugs and lose that war miserably. I mean, so you grew up in the Netherlands. Was there a drug, awareness program? I mean,
you have coffee shops.
yeah, exactly.
So you go to, I don't know, Amsterdam and you can try out some legalized pot, you know?
Yeah. I don't know. The U.S. is just doing this all wrong, and this game is an unfortunate byproduct of the war on drugs. So, yeah, take it for what it's worth. So, how do you get the temperatures close to 0 K not in space? That's a good question. So, you measure at, what did we say? It was 0.1 Kelvin? No, you're at millikelvin, right?
Yes, I'm at
0.001
millikelvin.
Kelvin. How do you get to that temperature?
So you use both helium-4, liquid helium-4, which can go to 4-ish Kelvin, right? 4.2 Kelvin is its boiling temperature. And that's how I jump. And if you pump on it, you can also get it to 1 Kelvin, right? You're using pumping to reduce the vapor pressure.
That's interesting.
And reduce the boiling temperature, right? So you can go get it to about 1 Kelvin-ish, okay? And then you can also use helium-3. And then you will get the same idea, different isotope, right? So now you can cool something to probably about, with pumping, you can go to about 300 millikelvin or so by using helium-3. And then if you do something clever with a mixture, so it's called a dilution fridge, then mixture of helium-3 and helium-4, and you pump on it, you can get down, if you do your very best, to about 20 millikelvin for quite a long time, until your helium-3 for helium-4 mixture sort of evaporates too much and you lose your mixture.
So that's the mixture. Is that colligative properties? I don't know if you use that terminology. That's freezing point depression type behavior, or how does that work? Why does the mixture? It's entropy driven.
I think so. Yeah.
That's interesting.
So we run helium-4 systems, helium-3 systems, and then dilution fridges as well. Well, I don't run them. We use them, but they run them at the Mac Lab.
Oh, now that's crazy cold. I think the lowest we go with most of our stuff is just liquid nitrogen, 77K. So when you're using helium, is it direct contact, or you have a gas contact agent? How do you actually translate that?
Oh, to your sample?
Yeah.
Well, actually, the sample is then immersed in this mixture. So usually have it in your sample
I see.
chamber, or
It's directly. Okay.
not for all systems. Sometimes it's a cold finger that's connected to something, but sometimes you do have your sample actually inside the cryogen as well. So it depends on the design. Obviously, if you can immerse it, you can get a lot colder.
Cuddle Puppy has a suggestion. Hey, a unionized worker to do something. They move so slowly, all the particles around them will also cease to move. It is Labor Day week. You are not allowed to criticize unions, as they are the reason we have weekends and we can't get fired for getting hurt on the job. Sorry, Cuddle Puppy. We're going to defensive unions. We have a faculty union at FSU.
We do, yes.
Protects us if something happens, because the university won't necessarily. So, I only have access to DMV workers. Will that work? Sorry, DMV workers in the chat. We are not responsible for the things said by members of our chat. Christianne, what do you think about NARC so far? Is it everything you hoped it would be?
Obviously, yes.
This is what the war on drugs
I seem to be walking far
Yeah.
I should have taken the car, but I collided with something.
So this is the longest and slowest level in the game.
I see.
Unfortunately, and you have to memorize the car pattern to beat it. And there's some randomness where those bombs show up. So this is kind of a pain in the ass speed run. So, Pullman rail car strike. Just look it up after a trivia question. Now that's one of the things. There's a really great line. Something about like all regulations and union and rights for workers have been written in blood. Like somebody had to die, somebody had to suffer, somebody had to go on strike to get us those privileges. For example, weekends and healthcare and medical leave and all sorts of stuff that we wouldn't have otherwise. So, So the free market capitalism fails us in many aspects. Unions combat some of those failures. So I will defend unions. Do you do other science outreach communication as well? I guess that's a question for you first.
Yeah, actually, I do things like taking on, colliding with whatever that is.
No worries.
Taking on high school students, right? Mentoring high school students and undergraduate students. So that's also
Go to the bottom and just walk. Yep.
that's also outreach of some kind, right? I've been in classrooms doing, like middle school classrooms doing demos with electromagnets, for example.
That's fun.
Like a class, not really a demo. They're actually doing they're building electromagnets themselves, with and then measure their strength with paper clips and stuff.
So they put copper wire around a nail and
Yeah, essentially.
that's fun.
So yeah, those things, and then I do a lot of outreach associated with like trying to recruit minorities, underrepresented people from underrepresented backgrounds, and also women in into STEM areas. So that's also something I do on a somewhat regular basis. It's been a bit less since COVID, but yeah.
On a related note, so my group right now is 6 female students.
Wow.
Yeah, in chemistry, which is kind of crazy.
That is crazy.
Yeah, just statistically, that's very unlikely. But yeah, just by coincidence, who was interested, who wanted to join.
That is nice, yeah.
And I'm sure like there's certain bosses you might not want to work for as a female and things like that. I don't think it's bad in FSU chemistry as far as I can tell, but again, unusual.
Yeah,
So you're gonna go in the last door. So
Okay.
if you go here,
I was trying to get some of these clowns.
that door, and a car, and you'll get a silver card in this room if you go to the right.
Go to the right. This is right.
They want to work with you because you're so dreamy. That's clearly the answer. Thank you, Cuddle Puppy. As usual. All right, you're going to press up, but not too much. Oh, and you go back in the room. It happens to everyone. It's poorly designed. They shouldn't put you out directly in front of the door. But after you go through the door, push it down, and then, yeah. Just go through. Yep, and then go left. Key card door. Right over there.
Oh. Did I go in the wrong door again?
Yep. You want to go to the next door over to the left.
How do I get
Watch
away
out
from
for
the killer clowns?
with
My goodness.
Because that's what we learned about in Dare. That was part of the drug dealing endeavor. All right, we're going to do...
So the blue door here?
Blue card. Yeah. So you got to you just go up to that thing. You have the card already.
Okay.
Or sorry, not blue card, silver card. And then go through the door. There we
I
go.
see.
It's not... The gameplay is not as friendly as, say, Mario. But so it goes.
Details.
Yeah. So actually, do you guys have Gordon Research Conferences in physics?
Yeah.
GRCs?
Yeah.
So are you familiar with the GRSs, the graduate seminars, the student-only portion before GRCs? I don't know if
I've heard of it, but
okay.
yeah.
But I got invited to the Donor Acceptor Electron Transfer Conference
that's
at
nice.
the GRS. I got to talk about science communication and stuff. And so I actually got to talk about Ask a Scientist outreach online. This is the only level where you're going to go left.
Oh.
But it was really fun because it was like students only, but I had this existential crisis when I realized that I was the oldest person in the room.
Oh.
At 40 years old, I was the senior most member of that room. So here you'll have to shoot the Rambo guy with bullets, reasonably close range. One of them will eventually drop a green card. So you have to let them come at you a little bit. If you shoot them from too far away, for some reason it doesn't drop the green card. I don't know how this works. Not figured out the rules on this. There we go.
There it is.
Nice.
Maybe you need to be shot in the back. Who knows?
Yeah. I've spent way too much time playing this game, actually. This started as a joke. All right, Huggy Bear has a question. Superconductors and magnets do all sorts of things like quantum locking. Do you have any other fun magnet tricks that we don't usually get to see? Besides floating frogs, are there any cool magnet tricks you can talk about?
You think about that. I thought the floating frogs was pretty neat.
Huggy Bear, I don't know if you were around for the floating frog discussion, but Jim Brooks at the Mag Lab basically put a frog in a 45 Tesla magnetic field and floated a frog. Basically induced fields within the frog, which is kind of a cool trick. But
so, I mean, you can float, if you have a high TC superconductor, you can float a magnet on top and it will be, that is like, you don't need a high magnetic field and you can float the magnet and it will be quite stable there, locked in by the field line, so to speak. And then, until the TC is reached, basically, because of course you'll need liquid nitrogen or something to cool the superconductor to keep it afloat, the magnet. But that's, how you can essentially, levitate something rather permanently, as long as you can keep the superconductor cold. And it can rotate, and
that's a demo now, right?
It's pretty standard.
Nitrogen over it,
but that's definitely, I would say, cool. And it doesn't require high magnetic field; just requires a magnet, permanent magnet, and a superconductor.
Yeah, it's pretty fun. But Huggy Bear was not here for the frog discussion.
Okay, well, that's definitely also next.
Floating a frog in a pool. Also, MRIs, those are dictated by magnets. Fields are everywhere. What else did we go down? The strongest magnetic field in the universe was a neutron star at 1.6 billion Tesla, which is absolutely astounding.
Oh, I already had the card. Okay.
Yeah, you have the blue and the red card. Sorry, I'm focusing on the questions, but that's fun. That's why I like the request a factoid, because you can usually drop just a crazy knowledge bomb on someone that's never thought about stuff like this, which is really fun. All right, I got to squeeze in one of our last standard questions. What's your favorite equation?
Well, I have a most used equation for sure.
Maybe your least favorite.
It's very useful. It's Bragg's law.
Oh, really? That's
because I do a lot of diffraction, right?
I literally covered that in Gen Chem today.
Oh, well,
yeah,
there you
X-ray
go.
diffraction, Bragg's law.
It's a really useful and really easy to use equation.
And that's for your neutron diffraction? What is that?
Well, I mean, definitely, everyday basis is more X-ray diffraction, but the same diffraction laws apply for neutron.
That's
Things
cool.
get a little bit more complicated to model, but you can still calculate, the angles at which you expect diffraction peaks to occur with that equation. So it's very useful. Also like the structure factor calculation, where you, by knowing the atomic positions, you know exactly which peaks in diffraction pattern should show up and how strong they should be. So that's useful. So yeah, I like those because they're very useful, and we use them a lot. But one also has to love Schrodinger's equation.
It's a classic.
Yeah. Definitely. I don't like these dogs very much. They're
So,
hard.
fun factoid related to Bragg's equation. Actually, one note, you have to shoot the guy in the wheelchair with a rocket.
Okay.
It's going to be tap A. There you go. And he's going to inchworm. Fun factoid on Bragg's law. That was the father-son combination. It was William and Lawrence Bragg. Father and
still
son
don't have the
figured out
card.
X-ray diffraction, so you have to do it 2 more times.
Oh, okay.
So you have to, with a rocket. So you don't have to jump with this guy.
Oh.
This guy's just shoot with rockets. But the son was actually 25 years old when he got his Nobel Prize for X-ray diffraction, which was the youngest Nobel Prize winner, I think, up until recently when I think it was Malala broke that record, which is kind of fun.
Well, then I like the equation even more now.
Yeah, so that is your favorite, or that's your
Yeah, why not? Well, maybe that
super
it's an
useful.
elegant.
And that's one of the things I tried to express today, because we talk about solids and crystalline solids, and it's it's such a simple equation.
Yeah.
It's just, and you take an X-ray
Easy
pattern.
to teach.
Yeah.
Easy to directly apply to actual data, so students can start thinking about data critically and extract quantitative information from it. It's it's very elegant.
Yeah.
The way you can calculate, the angles and the structure factors.
And it's conceptually not very hard. All right, so here is the final phase of Mr. Big. What I recommend doing is going to the top of the screen, getting away from him, and then you have to jump and shoot him in the hat. So if you run like to the right, we'll say, run a certain distance away, turn back, and you got to jump and rocket in the air. Then I'd run away again and keep trying it until you get it to hit the hat. It is a pain in the ass. This is the worst part of the speed run. Well, one of the worst parts of the speed run.
That I have to do. Am I hitting him like that? Or?
So you're hitting him a little bit too low. So the rocket has to come out in the air, hit him in the hat. That was really close. If that would have been a little lower, that would have hit him. But yeah, it's basically this over and over again. That one was really close too. Slightly later on that. And you go around.
Because I have to go away from him, right?
Yep. If he's next to you, you can't do it. All right, last 10 minutes or so. If anyone has questions for Christianne Beekman about magnetic materials, about low temperature or high magnetic field measurements, about 2D materials, about pulse laser deposition, about anything condensed matter physics, even some astrophysics, we can throw it in there at the end of the night. If you have questions, throw them in chat. We are happy to answer them while she faces the final boss of NARC and wins the war on drugs. Ooh, that was very close.
I don't know my timings quite right.
No, it's understandable. You have literally never seen this game, or there it is. Okay, now it's just to the face, no jumping. There you go. Okay, now it's just bullets. So you're gonna have to essentially walk around, walk away, but you can't shoot them at the top. You have to move down a little bit. It's just bullets. So you can just hold the bullets and unload on them. Sometimes they're gonna hit and sometimes they won't. All right, final phase of Mr. Big. This is your guys' last chance. If you guys have any questions, throw them in chat. We're happy to answer them, including about favorite equation. Bragg's equation is really fun. That's what I just coincidentally literally taught today, which is kind of cool. Oh man, what else do I want to ask? I have a few standards that I really like to throw in there. What is the Earth is flat / anti-vax equivalent in your field? Is there some lunatic opinions? Monopoles exist, or
Well, maybe that's it, right?
not necessarily the scientific community or general public misinterpretation. I mean, one of them is like magnetic bracelets curing diseases.
Oh,
like
okay,
that.
yeah.
Like that might.
So I heard once, I don't know, maybe it was even at the Ask the Scientist that Real World Square once. I'm not sure that people thought that the mag lab would influence weather patterns. Sort of the high magnetic field.
That is a running joke on Reddit, actually. Anytime they get a snapshot of the radar where it's like the weather doesn't go around Tallahassee, they're like,
magnetic. The mag lab has a magnet on, and it's attracting all the rain or something like that.
There it is. Go right. Find the exit. Ladies and gentlemen. All right. Now you're on to civil forfeiture, the level where you get to steal gold without due process. So yeah, the full picture of. Also, you're on a timer, so just.
Oh, okay.
You don't have to get the gold.
Okay.
I get so many geoengineering conspiracy theory emails. That is an interesting listserv to be on. I don't know how you found that, Miranda, but congratulations. All right. 20 minutes and 46 seconds. Do you want to know where you sit on the compendium of guest performances? It's 2046. We all know magnets work by tiny elves wearing their magnets. Absolutely. You were at, what do you got? 2046. That puts you at 5th on the leaderboard. Yeah, 5th out of, how many guesses?
Well, I'm proud of that accomplishment.
No,
for sure.
That's amazing, actually. Your first time playing that, and not playing Nintendo in 20 years, you absolutely tore it up. So out of 30 guests that have played this, you are 5th. Congratulations.
Who's number 1?
It's Alex Robb, one of my former grad students in chemistry, and then Rob Lazenby, a new chemistry hire, and then Justin from chemistry. He did it twice, so that's kind of cheating. But congratulations, you can put your initials in.
Oh.
Magnets work by Gandalf switching franchises. Absolutely. I don't know enough about magnets to say otherwise, so we're going to say that's a true statement. All right. Oh, well done. 2046 with no assistance of any kind. So congratulations. At the very least, you won the war on drugs tonight.
I'm happy that I did. Right. Made the world a safer place.
Yeah. Does anyone have suggestions on people we should raid? We have about 4 minutes if anyone wants to ask any last minute questions or wants to suggest somebody to raid. Other than that, any last minute comments for the audience? Any parting thoughts?
I think physics is cool, but science in general is also very cool. I mean, if I wouldn't have done physics, I would have done something else related to science. Almost became an astrophysicist, but then switched to condensed matter, actually. So I do have a love for astrophysics, so that's why I probably don't mind teaching it as well.
Did they ask you, or did they tell you were teaching astrophysics?
You know, they asked me, but as an assistant professor, you kind of do what you're asked sometimes, or all of the time, perhaps. So, I've told them now that I would prefer not to teach it anymore. If, I can teach condensed matter, I would totally prefer that, of course. But I enjoyed it when I was teaching it, sure.
So I'm looking at people to raid, but we'll figure that out. Maybe we'll go after stream. Stick around afterwards. Thank you all for joining us. I'm going to just quick do a description of our next guest. So I've been talking about for a while wanting to get somebody that's outside of the sciences. In fact, somebody that did like music theory. And it just so happens in 2 weeks, Juliana Grasso. So here's the descriptor. Critical and analytical methods in music theory, media studies, and cognition with particular interest in video game music.
Wow. Sounds interesting and impressive.
That's like a very outside their expertise. I'm genuinely excited. She actually streams on Twitch occasionally with various different music theory people. So
cool.
I mean, Nothing against people in the sciences, but I know what most of you guys do to some extent. But this one is going to be out there. So you guys, in 2 weeks, you should join us. 921 Julian Grasso is going to be our guest. But yeah, Christianne, thank you for joining me again. This is a
You're
weird
welcome.
ask. I'm glad you, hopefully you enjoyed your nostalgia kick with Mario.
I did.
And Punch Out. And you got to win the war on drugs with NARC. Who knew
I
that
feel
would be-
very accomplished.
That's all we can hope for during these streams. So thank you again for joining me. Thank you guys for all coming by. You better fix linking VIPs so I can link some amazing video game music. I will do my best, Cuddle Puppy. It's Nightbot is filtering you. I apologize. It's probably for the best, but I'll look at it sometime this week. But again, thank you for joining us. In 2 weeks, again, our guest will be Juliana Grasso, who's in the College of Music at FSU, does music theory, particularly related to video games, which should be directly relevant to our interest on our stream. But thank you all for joining us. We've gone through a journey of, astrophysics plus magnetic monopoles plus suspending frogs in fields and graphene and all sorts of stuff.
Strawberries even.
Strawberries in a magnetic field. We always enjoy the journey that you take us on, so we thank you for that very much. Stick around. We're going to find some kind of science streamer to raid of some kind. But until next time, thank you as always for joining us, and we'll see you in 2 weeks.